Okay, sorry. I think I was on mute. So now is this fine? Okay. Now I hope I'm audible and now things are fine, right? Okay. Sorry, I was on mute. So let me repeat that. What did I say? So today we are going to dedicate this entire day for computer networks, right? So we are going to study all of the concept in the computer networks. Okay. So I hope you are getting right. So we are going to study all of the concept in the computer networks, which means whatever is required to solve for gate questions. See, in one day, obviously we cannot cover the entire subject that is for one semester in engineering. But what we are going to try in this in this particular session or the multiple sessions for the today, we will be covering all the concepts that are required to solve questions. Okay. So what I can promise you, okay, let me just go through that what we are going to cover here and what I can promise you at the end of the today. So at the end of today, I promise you that if you attend all the sessions, okay, at the end of today. So if you attend all the sessions, then I promise you, this is my promise, that if CN is coming for, let's suppose, 10 marks, then definitely you will be scoring. I mean, I'll see in just one day. I cannot promise you most of the things. Like I cannot say that out of 10 you are going to score 10 marks, but I can definitely promise you that 5 to 6 marks you will be definitely securing if you do not know even anything in computer networks. Okay, so by just attending today's lecture. If you already know something, then obviously the chances of getting 10 out of 10 will definitely increase. So if you already know something, then 10 out of 10, this chances will increase a lot. Okay. Now, what we are going to cover is basically theory and plus, let me just tell you what we are going to cover. We are going to cover theory plus PYQs. So, in the theory, we cannot cover, obviously in one day, we cannot cover everything. So, that's why we will be covering just a required theory. Okay. Just a required theory plus PYQs. So this is going to be our focus for today. Okay, most of the good PYQs, almost all good PYQs we will be doing. Almost all good PYQs. So if you are repeating, which means if you have already done this subject and if you want to just revise, then I will say this session is must for you. See, the importance of PYQs is too much. It is very, very, very important that you do all of the PYQs. If time permits, then you do it twice. So let me tell you honestly that when I was preparing, then I did it twice. Like, I mean, maybe thrice. I do not exactly remember that if I did it thrice, but yeah, twice I remember, because one time, obviously everyone go through in depth. I have also went through. Then another time, okay. So at my time, I did it twice. Another time I have not went through all the PYQs, but yeah, most important ones I went through where I was finding the difficulty. So I will say that if you are finding any difficulty in PYQs, then you should be in this session, and in this session we will be focusing most of the PYQs, and also if any background is required, then we will be also covering that required theory. Okay, so this is the objective of these classes. And what is the target audience? Target audience is that if you have not studied anything, then definitely you can attend. Not studied anything in this subject, then definitely in this one day, okay, in this one day you might be able to attempt maybe 2-3 questions in the CN in the GATE exam. Okay, and the second point is that if you want to do PYQs in depth. Okay, so either you are this, which means you have not studied anything, then also like we will be covering the required prerequisites so that you are able to attempt a few of the questions. And also if you want to just do the PYQs, then this session is must for you. Okay, reason being is that we are going to focus on the PYQs mostly for today. I hope the objective is clear to everyone. Now let's just move. Okay, so let me know if you all are ready. So today we are going to start with the first topic, which is data link layer. Okay, So I mean today in the sense in this session. So since I'm not used to of the marathon, so that's why I'm just saying today. So whenever I say today, I mean this session. Okay. Okay. So the topic one that we are going to study will be data link layer. Then there will be a break. Then topic 2 that we are going to study is network layer plus some of the transport layer, some transport layer, and then there will be a break. And then topic 3. So there will be 3 sessions. Topic 3 will be your transport layer definitely. I mean remaining transport layer plus application layer. Okay. So there will be 2 break and there will be 3 sessions. Now each session I will try to finish this data link layer, required things in data link layer in this 2 hours, but it might go for 2.5 hours also. So that's why I'm writing it 2.5 hours. Okay. Each session might be of 2.5 hours. Now for the similarly for this network layer also, I will say I might take 2.5 hours. So let me just write it 2.5 hours there also. So here also I might take 2.5 hours. Here also I might take 2.5 hours. So this is the plan. So total we are going to study maybe 7 to 8 hours today. Just attend the session live. Whenever you have any difficulty, just let me know. Okay, just attend it. Like this particular day is completely dedicated for computer networks, and I will make sure that each and every query is resolved. Okay, so I will answer each and every query if you ask me in the chat window. Now let's just start with the first topic, which is data link layer. Okay, so let's get started with the topic, which is data link layer. Now in data link layer, what we are going to study is basically 2 things mainly, which are part of the GATE syllabus only. One is flow control, another one is error control. Okay, these are the 2 things that we are going to study in the data link layer. Now in the flow control, we are going to study some protocols which are called sliding window protocol and stop and wait protocol. So stop and wait protocol and sliding window also, like I mean the sliding window, there are selective repeat and go back end. So let me just write sliding window. In error control, we are going to see Hamming distance and CRC. Also, as a third topic, we are going to see today in this session. Today means in this session only, we are going to see networking devices, which means what is hub, what is router, and these things, right? What is the collision domain? What is the broadcast domain? Collision domain, broadcast domain, these things we are going to answer. So we will be seeing these topics in this particular session. Now 1 hour I will be dedicating to each of the topic, which means 1 hour here, 1 hour here, and then maybe it is very small topic, so it will just take 30 minutes. So that's my plan. Okay, so let's get started. Now the first topic is stop and wait and sliding window protocols. Now let me just quickly revise you that there are 2 times. One is transmission time, another one is propagation time, right? So what is a transmission time? Whenever there is a sender, if that sender is going to send something to the receiver, okay, this is receiver, then the transmission time says that how much time you are taking to put the data on the link itself, which means that if this is sender, if this is sending something, then how much time you are going to take just to put this data, okay, whatever data you have, just to put this data on the link itself, how much time you are going to take. That's called transmission time. Now what to which factor this depends on, since this will definitely depend on the bandwidth, I mean what is the bandwidth of the channel, and this will definitely depend on the length of the packet, right? If the packet is larger, then it should be transmission time should be greater. So that's why it is basically directly proportional to the length and inversely proportional to the bandwidth. Okay, so that's the formula of transmission time. It is, let's suppose in the bytes, I will say that these many bytes are my packet, and let's suppose it is bytes per second. Okay, bandwidth is, let's suppose, bytes per second. That means that this channel can transmit the data with this much bandwidth or bits per second, but let's just keep this unit same, bytes and bytes. Then finally this is in the seconds, right? So that's called transmission time. Now let's go to another part, which is called propagation time. So what is propagation time? Okay, let me quickly repeat you. If you think that things are repetitive, let me tell you that this is going to be worth, which means I will not take too much of time in the basic things, but if I'm just spending, let's suppose in 1 hour, if I'm just spending 10 minutes in the basic things, then I hope it is worth for all those who already know those basic things, right? So what is the propagation time? Propagation time is a time that you take, that a single bit take basically to reach from one end to another end. So the important point here is any single bit take TP time, which is propagation time, to reach from one end to another end, right? That is called propagation time. Now, why these two quantities are important? Because let's now let's now combine these propagation time and transmission time. So combining, and then you will see the magic that why these two quantities are important. Combining transposition time, propagation time and transmission time. Okay. So what do I mean by combination? Let me just tell you. See, suppose now a sender is sending something. Okay, this is sender and this is, let's suppose, receiver. Now suppose this sender is sending one packet. Now consider a packet which this sender is sending. Okay. Now what's going to happen? Since this is sending some packet, then it has to transmit the packet, definitely, right? So there will be a packet that is currently that is with the sender only. Okay. Currently that packet is with the sender only. Now the sender is going to transmit the packet, and then this packet will get propagated, right? Now currently this is the scenario. Now let me just call this scenario at t equal to 0. Okay. So yeah, just a second. So let's just call this scenario as t equal to 0. So what I'm saying here is that this is the scenario, and I'm calling this scenario as at the time t equal to 0. And then let's just see what's going to happen after some time. Okay, I want answers from you, and that's why I just request you to focus here only. So this is at t equal to 0. Now tell me, after transmission time, what's going to happen? You will transmit this whole data on the link. So after the transmission time, your packet might look like something like this. I mean, the whole packet is on the link, and then your packet will look like this. You will say that your packet is now looking like this, isn't it? Now just focus on the last bit here. This is the last bit, right? Let's just call this as a last bit. Now tell me how much time this last bit, okay, I'm not asking about the first bit. Remember, how much time this last bit is going to take to reach to the receiver? Let me know quickly. How much time this last bit is going to take? So if I just ask you that how much time last bit is going to take, you will say that it is going to take propagation time, right? So that's why now the scenario after, so this is basically scenario after t equal to tt. Now let's just draw the scenario, after t equal to tt plus tp. So t equal to tt plus tp. Okay, which means the transmission delay and the propagation delay. So this is the scenario after t equal to tt plus tp. Now you will say, since you are just asking about after the tp time also, which is propagation time, that's why this last bit must have reached to the receiver, which means this is the scenario of your packet, right? This is the scenario of your packet, isn't it? This is the last bit. This is the last bit. Now do you see that from the moment, okay, from the moment, which means t equal to 0, from the moment you start your transmission till the moment the last bit, even the last bit is received by the receiver, you take this much total time. Isn't it time important? I mean, this time is telling you that how much time you takes from the moment you even think about the transmission till the moment that receiver completely, okay, completely, this word is important, the completely gets the frame, completely gets the frame. See, this understanding is very important, that what this time is doing, okay, and then only you will be able to solve the questions. So I hope you completely understood this, that what it is doing. Now let's just see that why this time is even more important. Now we have got little bit idea that why it is important, but why it is even more important to solve the questions. Let's just see this. Okay. Now I'm saying that this is the scenario after t equal to tt plus tp. Now let's just see a scenario where I just ask you what's going to happen if the receiver is going to send some acknowledgement. Okay, let's suppose the receiver is sending some acknowledgement, then what's going to happen? So I want to check that scenario also. So let's just copy this, and then suppose that acknowledgement, we will be solving the question where acknowledgement will also be having the propagation delay, sorry, the transmission delay, but suppose the acknowledgement length is so small that it is not taking any transmission delay. So this is basically t equal to tp plus tt, right? Now I want to ask you what's going to happen after time t equal to tp plus tt. This is the time that you start your transmission till it completely get to the receiver, right? Plus suppose that it starts the transmission, but let's suppose the transmission time is 0 for the acknowledgement. If you want, you can definitely write that, but I'm not going to make the things complicated in the first iteration. We will make it little further advanced in the next question set of questions. But for now, let's keep the acknowledgement transmission time is 0. Now what is the propagation time of acknowledgement? It will take the same time, which is tp. So I want to ask that what's going to happen after t equal to tp plus tt, which is a packet transmission plus propagation time plus one more propagation time. Then at that time, if you are saying that one more propagation, if you are saying that acknowledgement width is almost negligible, which means acknowledgement is this much, let's suppose this much big, but this is very negligible. I mean, this is very small. Okay, small. Then in that case, small in the sense that I do not have a concept of last bit or first bit. I mean, acknowledgement length is so small that I'm just saying that okay, last bit, first bit doesn't matter because it is very thin. Okay, so here I will say that after TP, I mean, you consider last bit or first bit does not matter, but after TP more time, you are going to get the acknowledgement completely, right? So the sender is going to get the acknowledgement. So sender will receive the ACK, because the ACK length is so small. If the ACK length is not small, then definitely you can add the transmission time of the ACK here, and that's the time that you are going to take. So basically, this whole time is called round trip time. Round trip time means the moment you even start the transmission, see, this is the moment you even think about the transmission. Like, I mean, you just say that, okay, now let me send the packet, right? This is the moment. And till the moment, see, in between, there is a phase where you're saying this is the time till your first packet get reached to the receiver. So basically, if someone asks you how much time one packet take from to transmit and to propagate, completely transmission, complete propagation, then you will say TT plus TP. You should not be confused in this. Okay, this is the time for complete transmission and complete propagation. And then if someone asks you that, okay, let's suppose the acknowledgement transmission time is negligible, then how much time the ACK is going to take to come back to you? Then you will say just add TP time. So this is basically 2TP plus TT, right? This is the time that is the time that telling you that you think about the transmission till you get the ACK complete. Okay, so this time is extremely important. Let me just write it, 2TP plus TT. This time is very important. This is saying you that the moment you think about the transmission, think in the sense, I mean, you start, okay, think you can think maybe yesterday, you can think 2 years before also, but think here, I mean, I just want to convey that you actually start transmission, right? Think about the transmission till the moment you get ACK completely. And this is the time. This time is very important. This is called round trip time. Round trip time. Okay, I mean, this time is what you have in your hand. See, this time is what is in your hand. I mean, see, everything has a fixed time. I mean, for gate preparation, how much time you have? Let's suppose 1 year. Okay, from the exam that gate 2023 happens, and from the day that, let's suppose, gate 2024 happens, there is a fixed boundary, right? So let's suppose for gate preparation you have 1 year, right? For gate preparation you have, now you don't have 1 year obviously, but I'm just assuming that from the start you have 1 year. Similarly, if someone says that from the moment you start the transmission to you get the ACK completely, how much time you have in your hand, then you will say this is the time that you have in your hand. You are making use of this time. How, I mean, how you are making use of this time, how many packets you are sending, how many packets you are not sending, it is something, some different question, but this is the time that you have in your hand, and it means that you start the transmission till you get completely, okay, till you get ACK. Now let's just see that how to utilize this time. See, whatever time if I have, if I'm just wasting my time and not doing anything, sitting idle, watching movies, then obviously like I mean the gate preparation is not for me, right? Similarly, if I'm just not utilizing this time, maybe I'm just having very less efficiency. So let's just see that how to utilize this time. So there are different protocols which is called stop and wait. One is called stop and wait. Another one is called sliding window. Right, there are two different protocols. In the sliding window we have selective repeat and we have go back in. So there are actually three different protocols if you want to consider as three. One is this, another one is this, another one is this. Now it depends on that how we are utilizing this time. Now let me just tell you that how we can utilize this time in the best possible way. Okay, so let's just see. Now suppose that in this time, which is the time 2p plus tt, okay, this is the time. If I just ask you that my question, let's just listen this question properly. I want to ask you that how many packets you can send in 2p plus tt time. How many packets you can send in 2p plus tt time? Anyone can answer this question? Just let me know. Okay, let me just simplify this question first, and then I will ask you a different question. So basically, let me just ask you a question where I'm just saying, so instead of that time, I'm just asking you that how much time, how many packets you can transmit in 5 tt time. If I just ask you that how many packets you can transmit in 5 tt time, then what will your answer? Okay, do not give me answer which is, I mean, you already know of. You just apply your normal aptitude here. So how many packets you can transfer in let's suppose 5 tt time? So the answer is, see, there is always a delay in whatever I'm speaking and whatever you are hearing. That's how YouTube live works. It's not a problem with our end. It's how YouTube live works. So maybe whatever I'm saying, I mean, you will be hearing it after some time. The streaming is always having some seconds of delay. Okay. So Shurukirti and Pratik Jain both are saying, Muhammad Ali is saying 5, right? 5 is the answer. Yes, definitely. So how you did it? You basically took that time, which is 5 tt, and you divided by tt, and you are saying, see, the 5 packets you can send. That's how easily you can find, right? Now let me ask you a question where I say that instead of 5, if I say it is 10, in 10 tt, how much you can send in 10 tt, then what will you answer? Instead of 5, if I say 10, then you will say, see, 10 tt, whatever you have, let's just divide with tt, then you will say 10 packets you can transfer, you can transmit in 10 tt time, isn't it? So that's how easy it is, right? You just need to divide by what? You just need to divide by tt time. Now let me ask you a different question, okay, where I am saying how many packets you can transmit in tp time. Now this is going to be little interesting. How many packets you can transmit in tp time? Your answer will be how much? You need to divide by what? You need to divide by tt, right? That's how you did it earlier. Earlier it was 5 tt, you calculated it 5. Now it is tp, right? Now it is tp. So what you need to do? You need to divide that tp by tt. So basically earlier you did this. This is what we did earlier, right? Why we did this earlier? Because whatever time I had, divided by tt will give me the number that how many packets I can transmit in that much time. So how many packets you can transmit in tp time? You just need to divide by tt, right? So these many packets we can transmit in tp time. I hope you understood, right? Okay, let's just call this number as a. Are you getting? Let me know if there is any difficulty you are facing. See, just feel free to question me. If you do not ask me, then I will not get to know. Just feel free to ask me. So yes, Shurukirti, that's fine. This is TP upon TT. Now let's just do one thing. Let's just call this number as a, because this number is going to be very interesting number for our computer network purpose. Okay. Why it is interesting? Let's just see. Suppose that there is some channel, I mean there is some sender, there is some receiver. and I want to check that how many packets you can transmit in TP time, which I'm just calling it A. I mean, I calculated this number by TP upon TT and I'm just calling it A. So basically what I'm saying, let's suppose the sender is sending something and it is receiving the acknowledgement later. Now there is some packet that you have, right? And that you, so what you will do, you will take that packet. Let me just tell you here. So you are having some packet, you will take that packet and you will transmit that packet first, right? And then let's suppose this is the last bit. Then after some time your transmission will be completed, and then you will say that after some time, maybe you will be saying that my transmission is completed, and now let me just say that this packet has been completely transmitted, okay, which means this packet is now actually this, and this is now last bit, right? Now this last bit is going to take how much time? This last bit is going to take how much time to reach here? It is going to take TP time, right? So basically in this TP time, whenever this last bit is reaching here, how many packets I can put here, right? That's called TP upon TT time. So basically whenever this last bit, okay, whenever this last bit is going to reach at the end, which means it is going to reach at the end after TP time. So in the TP time, any bit, not just last bit, any bit reach to the end. In this TP time, okay, this is basically the time of TP. Okay, this is the time of TP. Then the last bit is transmitting from here to here. In this time, how many packets you can actually put here in the link? How many packets you can put? The answer is A, because this is TP upon TT. These many packets you can transmit in that much time. So basically in the link, when these many packets are there, if I just say how many packets are there in the link, then you will say this is A. A is the number of packets that will say that you are going to have a number of packets in the link. Can you have more than A packets? No, right? I mean, the moment this is reaching here, you can put A packets only, and this is the situation that you have currently, right? So basically A is called capacity of channel. I mean, these are the number of packets you can put in this TP time. That's all. Okay. So I hope you understood this. Now let's just see that how we are going to have, how we are going to enhance this concept for the RTT. Now let me just go back to the question that I started with. Okay. So I think I started with the question, which is this: how many packets you can send in 2p plus TT time? How many packets you can send? Can anyone tell me? See, in TP time you are sending TP upon TT. In 5TT time you are sending 5TT upon TT. In anyway, in 10TT time you are sending. In 10TT time you are sending these many packets. Now my question is that in this much time you are sending how many packets? That's the only question I'm asking. So I think the answer is very easy, right? What is the answer? 2TP plus TT divided by what number? TT, right? These many packets you can transfer, which is 1 plus 2 TP upon TT. And since I'm just naming it A, so this is basically equal to 1 plus 2A, right? So in this time, which is called RTT, round trip time, okay, in this round trip time, we are able to send, we can send, whether we are sending or we are not sending, it will depend on the protocol, but we can actually send, right? So that's my whole take here. So let me just say that in 2TP plus TT time, this is very important time, remember, okay? We can send, we are sending or not, it will depend. We can send equal to 2TP plus TT upon TT, which is equal to 1 plus 2 TP upon TT, which is 1 plus 2A, 1 plus 2A packets, right? These many packets we can send. We can send. See, remember, this is can, which means we are sending or not sending, it will depend on the protocol. Okay, great. Now, I hope you understood this. Now, let's just move to the questions. Before that, I will just recall you some definition of bandwidth, definition of throughput, definition of efficiency. So, have you understood this, that how we are utilizing this time? See, what is this time? Let me maybe quickly repeat it, because why I am repeating it, why I am emphasizing is there is a reason. Because almost every question we are going to do is basically just based on this fundamental definition of 2TP plus TT. What we are doing in this 2TP plus TT time. Okay. I mean, whatever question, whatever numerical we do, we are going to just hit the fundamental, which is 2TP plus TT. So, what is this 2TP plus TT? Can anyone tell me? What is this 2TP plus TT? From where I am writing this time? This is the time. This is the time to transmit, or maybe time, since time from the moment we start the transmission till we get the ACK completely. Right? This is the time. In this time, we can send. Okay, this is the time that we have in our hand. Basically, I mean, we can utilize that much time. Just like a gate preparation have 1 year. Similarly, this is the time we have since we start the transmission till we get the ACK. This is the time that we have in our hand. Now it is up to you that how we are utilizing this time. So I will say that in this time we can send 1 plus 2A packets. Right? Great. Now, in the similar term, can you tell me that what is this TP plus TT time? In the similar term, can you tell me what is this TP plus TT time? What is TP plus TT time? Let me know. See, this is the time from the moment we start the transmission till the first packet is completely reached to receiver, right? So basically, this is the time to send a packet. You can just say, let's just avoid this transmission and propagation terminology. This is the time to send a packet. Time to send a packet, basically. Time to send a packet. This is the time that I need to send any packet. Suppose I want to send ACK. Okay. Suppose that I want to send ACK. Now here, suppose I want to send ACK. Now, how much time I will be, this B will be taking, let's suppose this is B, this is A. How much time B will be taking to send the ACK completely to A? You will say that it is TP plus TT. So here TT will be TAT ACK, I mean for the ACK, right? If this is 0, then you will say that only TP. If this is not 0, then this is TP plus TT ACK. So basically, this is the time that you will say this is the time to send a packet. Okay. So Muhammad is saying time taken from transmission of the packet to reach the receiver. Yeah, that is correct. But in simple terms, just think like that. This is the time to send a packet. Okay. If someone asks you how much time you will be sending a packet from one host to another host, you will say TP plus TT. That's all. Right. So Pritik is saying time to put on the transmission line till it reaches. Yeah, that's also correct. Swapnil is saying only the first packet will take TT plus TP time. Rest all will take TP time. Okay, that will depend on the protocol that we are using. Now currently we might not be sending multiple packets at a time. I mean, it depends whether we are doing the pipelining or you are not doing the pipelining, right? Anyway, have you understood that how much time you will be you are going to take to send a packet? That is TP plus TT. Okay, great. Now I hope you understood this. Now you know these two times. This time is basically time to send a packet and to receive the ACK. This is just a time to send a packet. Okay, so that's the difference between these two times. Cool. Now let's talk about, so now you know this time, now let's talk about efficiency, throughput, these two terminology. Okay, so let me first talk about the efficiency, then we will talk about the throughput also. Cool. So this is the time to completely get the ACK, number of packets that we can send. Okay. Now before I go to the efficiency, maybe I can drive the efficiency directly from this time. How? See, this is the time that is very crucial to me, right? Now someone asks you that how many packets you are sending in this time. What you did? You just divided this number by TT. You said this is plus TT upon TT. This is what you did, right? You divided this number by TT and then you said that's how we are going to get this, which means 1 plus 2a. So these many number of packets we can send. Now if someone asks you, okay, that's fine, that number of packets you can send is 1 plus 2a. Now can you tell me how many bytes you can send in this time? See, I have this time with me. Now I will be again and asking a question that how to utilize this time, or how to manipulate this time, or how to find out that what we are doing in this time. See, these are the number of packets we can send, and can anyone tell me how many bytes we can send in this time? How many bytes? Not in number of packets. I'm not interested in number of packets. My unit is bytes. I'm just changing my unit. Okay, it is here packets. Now I'm just changing my unit. I'm just saying the number of bytes we can send. Anyone? So Swapnil is saying only the first packet is okay. That's fine. Alok is saying that the time taken for the packet to reach receiver from the moment the transmission of the packet. Yeah, that's fine. Great. So Subhadeep is saying 2 TP plus TT into bandwidth. Great. So that's the right answer. So how many, if I just ask you what is the time, in this time, how many bytes you can send, then to calculate the bytes, see, to calculate the number of packets you divided by TT, that's fine. But now I'm asking to calculate the number of bytes. Now what you need to do, let me just let me just simplify this for you, and then I will come back to this question. Okay, so let me just say that in let's suppose the bandwidth, okay, bandwidth is maybe 500 bytes per second. Let's suppose if I just ask you in 2 seconds, 2 seconds, how many bytes you can send? Then what is your answer? What is your answer? How many bytes you can send? Then you will say, okay, in 1 second if I can send 500 bytes, then why not I can send 2 into 500. 500 means just a bandwidth, right? Is this fine? Now similarly, if I just ask you that in 100 seconds, or maybe in some time, maybe in TT, or maybe anything, okay, in TT, how many packets you can send, how many bytes you can send in TT time, how many bytes you can send? If I just ask you packet, then you divide it by TT. But now I'm saying TT time means seconds. Okay, just consider that this is same as this. I mean, these are the seconds. It is also in the second. So what you will do? So in 2 seconds you are able to send 2 into bandwidth. Then in TT you will be sending TT into bandwidth, right? So you will be sending these many bytes. These many bytes. Is this fine to everyone? Okay, so if you want to know that how many bytes I can send in that time, then I will be multiplying by bandwidth. If I want to know that how many packets we can send, then I will be dividing by transmission time. So that's how we will be doing. Now let me just relate it very nicely. Okay, so in TT time, let's suppose this is the time that you have in your hand. Okay, I mean, just I'm taking one example. How many packets you can send? Number of packets is equal to TT time that you have upon you divided by TT, which is 1, right? And similarly, I ask you the second question, how many bytes you can send? Number of bytes we can send. it is equal to TT into bandwidth, right? That's what we did. In 2 seconds we can send 2 into bandwidth. In TT time we can send TT into bandwidth. Isn't it same? See, TT into bandwidth is basically, if you just put the TT answer, TT is basically length upon bandwidth, right? So let me just write it, length upon bandwidth into bandwidth. This is equal to just length. I mean, L is the bytes, right? So if you are sending one packet, it is same as saying you are sending L bytes, because one packet is of L bytes, isn't it? Are you convinced that these two things are making sense? If someone asks you that in this time, see, every of this question in the flow control, either it is stop and wait or sliding window, every of this question will revolve around just this concept that, okay, what you are doing in this time, what you are doing in this time, and that's how we are calculating the efficiency, that's how we are calculating the throughput. Okay, so every of this question will revolve around just two things: how many packets you are sending, how many bytes you are sending. Someone asks you how many packets you are sending, just divide by TT. Someone asks you how many bytes you are sending, multiply by bandwidth, right? And these two things are exactly same. Now let me just ask you the earlier question which I started with, that if you can send these many packets, which is 1 plus 2a, then how many bytes you can send? Just multiply by the bandwidth, isn't it? So you are going to send bandwidth into 2TP plus TT. These many bytes you can send. So that thing is also very important. I'm not asking you to remember anything. Okay, do not remember anything. I urge you to not remember anything. Reason being is that in the question they will be manipulating many of the things. They will not be saying that only transmission time and propagation time is there. In the question they will say the queuing delay is there, the processing delay is there. Then what you need to do? You don't care about that whatever delays you have. You just say that, okay, whatever delay you have, okay. I mean, see, let's suppose that you have the queuing delay, you have the processing delay. Obviously you are going to have the RTT, which is, I mean, the transmission time and the propagation time, right? So this is what you are definitely going to have. So whatever delays you have, you just add it to your to the number that you have. This is the minimal number that you are having, right? This is the minimal. This is the minimal thing, minimal time that you have. But if you are going to spend time in queuing delay, you are going to spend time in processing delay. You are going to, let's suppose, spend time in suppose in the transmission time of ACK also. Okay, so whatever wherever time you are going to spend, you just add all of those times, and they will ask you what is the throughput, what is the efficiency, and they will try to make this complicated. You just add all of this time. Then if they ask you how many packets you can send in this time, you just divide by TT that time. Okay, just divide by TT. They ask you how many these are the, so let me just call it capital T or something. Okay, so let me just call it capital T, or maybe let me just call it time, total time. Okay, let me just call it total time. Total time. So total time, if they ask you in this time how many packets you can send, you will just say that total time upon TT, these many packets you can send. If they ask you in terms of bytes, you will say total time into bandwidth, these many bytes you can send, right? So now like whatever they ask you, you do not need to remember the formula, you just need to remember the concept. I mean, that's how you are going to solve those questions, right? Now they will not ask you just the packets and bytes. Instead they will ask you what is the efficiency, what is the throughput, these kind of terms they will ask you. Now let's just check about these terms. First is efficiency. Let me know if things are making sense and you are getting whatever I'm teaching you. If there is any doubt, you can quickly ask me, and then we will proceed to solve your doubt. Otherwise I can continue. Okay, good. So what is efficiency? Efficiency in simple terms, let me just define in the simple terms, and then I will tell you that this efficiency can be calculated in many ways. Okay, so depend on the question. So let's just focus on the concept. Conceptually, let me just define it conceptually without using any formula. Okay, conceptually, what is the efficiency? Efficiency means how much efficient you are, isn't it? Efficiency, simply it means that how much efficient you are. I mean, that's all. I mean, efficiency means that is all, like how much efficient you are, which means out of the total time you had in your hand. Okay, if you are wasting the time, then obviously your efficiency will be less. The total time in your hand, total time in your hand, and then in the numerator is that how much time you are utilizing. How much time you are utilizing, isn't it? This is just one formula. I mean, that's just a one way to look at the efficiency. There could be many other ways, which means instead of time, if we just say that how many packets, total packets you could have sent, okay, in the numerator, the packets you are actually sending, packets you are sending, right? This is another way of looking at efficiency. I mean, in terms of packets, okay, maybe in terms of bytes also you can say. I mean, all of this is same, okay, all of this is same. I will come with the mathematical formula also, but currently I'm just telling you the intuition. Another way of saying is that the same thing, okay, the bytes you are actually sending, instead of packets you can argue about the bytes also. You can say how many bytes you are actually sending and total bytes that you can have sent. That's also efficiency, right? How many bytes you are actually sending, total bytes that you can have sent. That's also efficiency. These two are efficiency, and this is exactly same in terms of time also. Okay, how much time you are you were having, and how much time I mean you are actually utilizing. So which means this thing, and these two things are also same. In fact, these three things are same. I will prove it mathematically also. This formula, these three formulas are same. We will prove it mathematically, which means we will find the efficiency using this formula. I mean, with respect to the time, we will see what is the efficiency. With respect to the packets, we will see what is the efficiency. With respect to the bytes, we will see what is the efficiency. Then finally, we will just conclude that, see, all of these are coming up with the same number. Okay, so let's just see how much time you are utilizing and what is the time that you have in your hand. So let's just talk about this first thing. So what is the time that you have in your hand? Tell me, what is the time that you have in your hand and how much time you are utilizing? So let's just first talk about the stop and wait protocol. Okay, so from now I'm first going to talk about the stop and wait protocol. Which means I will be sending a packet, I will be stopping myself, waiting for the acknowledgement, and once the acknowledgement is received, I will be sending the another packet. So one packet at a time, right? So it means one packet at a time. That's called stop and wait. Send a packet, stop, and then wait for the acknowledgement to come. Once the acknowledgement is coming, then I'm sending another packet, right? So how much time you are utilizing? You are just utilizing TT time. I mean, in this TT time, you are doing something which is the transmission, and then what is the time that you have in your hand? You have the complete this much time, right? This much time completely that you had in your hand, and this is the time that you are utilizing. So that's what efficiency is with respect to time. Now let's just see the same thing with respect to the packets that you are sending. Okay, now let's just see the same thing with respect to the packets you are sending. So how much packets you are sending? You're just sending one packet. You're just sending one packet. And how much packets you could have actually sent in the given time? Do you remember? In 2TP plus TT time, how much packets you could have sent? Divided by TT, which is 1 plus 2a, right? So 1 plus 2a you could have actually sent, but you are just sending one packet. So this is 1 plus 2a, right? So this is with respect to time. Let me just check with respect to bytes also, with respect to the bytes. Okay. So how much bytes you are actually sending? You are just sending one packet, which means L bytes. And how much bytes you could have sent in 2TP plus TT time? Can you just quickly tell me how much bytes you could have sent? You need to multiply by bandwidth, right? Okay. So these are the three formulas that we get. Let me just quickly check whether these three formulas are mathematically same also. Okay. So let's just check whether these three formulas that we just had are mathematically same or not. So tell me with respect to time what you got, how much time you are utilizing, just TT, and how much time you actually have, 2TP plus TT. This is with respect to time. With respect to packet, you are sending one packet, you could have sent 1 plus 2a packet. With respect to bytes, you are just sending L bytes. You could have sent 2TP plus TT into bandwidth bytes, right? So if you compare these three actually same. See, L upon bandwidth is just 1 upon TT, right? So this is basically, this is same as this. And then if you divide by TT here, this is just 1 plus 2a. This is 1 upon 1 plus 2a. All of this is same. All of this is exactly same. Let me know if you have understood this. Right? Okay. Cool. So basically, this definition I have taken from Wikipedia. Round trip time, as you know, that this is the time, is the amount of time it takes for a signal to send plus the amount of time it takes the acknowledgement of that signal to receive. Okay. So it includes the propagation time for the path, and basically if there is any processing delay, any of the any other delay, queuing delay, processing delay, or whatever, right? Everything is coming under the round trip time. So in general, round trip time could be you are sending some packet, transmission time it will take, then you are propagating, maybe some queuing delay, right? Queuing delay, and then maybe some processing delay. This is the time to send a packet. Then that ACK time to like send an ACK plus TP. This is the time to send an ACK, right? Time to send a packet, time to send an ACK, and then I mean, if whatever the delays that you have, you just include that in RTT, right? This is round trip time. Round trip time means the amount of time it takes a signal to send plus the amount of time it takes the acknowledgement for that signal, acknowledgement of the signal have been received, right? So that's the total time, which is called RTT. Cool. Now, I hope you understood what is efficiency, and efficiency of stop and wait is 1 upon 1 plus 2a. I will say, if you want, you can remember this formula. Otherwise, you should not remember this formula. What you need to remember is this, that you are having 2TP plus TT time in your hand. Because in the questions, that is not necessary that you are going to have this much time only. Okay, they may add some other delays, and it will be very confusing if you directly use the formula. So that's why I will not ask you to use the formula directly. You just know the concept. What is efficiency? How much time you are utilizing? You are always mostly, or you always in the stop and wait, you are just going to utilize this much time. How much total time that you have? Now it will depend on the question to question. What is the total time that you have? Okay. So sometimes, or maybe most of the time, it will be this one only, but sometimes this will be queuing delay, sometimes there will be processing delay, like that, right? So the efficiency will be this in that case. Okay. So I hope you understood that how we are going to calculate the efficiency. Time you are utilizing upon total time that you have. And every other formula, maybe I mean, in terms of packet, the packets you are sending, packet you could have sent, right? I mean, actually, all of this is basically coming from the time only. Like once you know the time, that this is the time that you have, right? Once you know the time 2TP plus TT, from this only you are calculating number of packets, number of bytes, and so on, right? So this time is important. And I will say, just remember for the efficiency, just remember the first thing, that with respect to time, how to calculate the efficiency. Actually, with respect to time, it is very, very important, because time will be changing, and then once time is changing, then everything else will change. So with respect to time, just find out the efficiency, right? So what is the efficiency? This was an efficiency. With respect to time, always calculate with respect to time, which means how much time you are utilizing upon how much total time that you have. Cool. Now let's move further. Okay. Now let's talk about the throughput. Throughput is basically number of packets per second, or maybe number of bytes per second, or number of packets per minute. So basically all of this is throughput unit. Efficiency was not having any unit. It is just a percentage, that how much efficient you are, 30%, 40%, 50%, like that, right? Throughput is actually having some unit, which is packets per second, or bytes per second, or packets per minute, like that, right? It will be having some unit, right? So I say that throughput is 5 packets per second, which means that I actually want to measure that in 1 second how many bytes or how many packet I can transmit. That is called throughput. I hope you understood. Now let's just see that what is the throughput in stop and wait. Okay. Have you understood what is the meaning of throughput? Have you understood that what is throughput? Okay, so Shubhadeep is saying, why is TP not useful? Which TP, Shubhadeep? Shubhadeep, which TP? I'm not getting. So I have not got your question. Let's just see what is throughput in stop and wait. What is throughput basically in general? Basically, it is a measurement measure to check how many bytes or packets. I mean, it depends how we are basically measuring bytes or packets we are transferring, we are sending in 1 second or 1 minute, like that, right? 1 second. I mean, it will depend on how we are measuring, or minute, or like that, right? So basically, like, how many bytes or packets you are sending in 1 second. So let me just take bytes and second. So how many bytes you are sending in 1 second? That's what throughput is. So I think it is very easy to calculate throughput in stop and wait. How? See, you are sending how many bytes? L bytes, right? L bytes. In how much second? 2 TP plus TT time. See, this time is very important. Again, I am saying this time is very, very important. You are sending L bytes in 2 TP plus TT time, isn't it? What does this mean? You are sending 1 byte in how many seconds? In I mean, see, throughput is basically bytes per second. So basically, it means that in 1 second, how many bytes you are sending? So or in other words, you can write like that: in 2 TP plus TT seconds, you are sending L bytes. L bytes. Now tell me, in 1 second, how much you are sending? That's the throughput. In 1 second, we are sending L upon 2 TP bytes. So that's the throughput, isn't it? Very easy to calculate once you understand the fundamental. See, if we even go to the go back and sliding window, these fundamentals will remain same. Okay. So the throughput is L upon 2 TP plus TT, which is in stop and wait. This is actually, I mean, throughput, since throughput is having some unit, so that's why I'm writing the unit also, because it is good to write the units. It is basically in the bytes per second, isn't it? Let me know if that is fine. Can you find the throughput in packets per second? Okay. So in you will say, in this much time you are sending one packet. In this much seconds, right? In this much seconds you are sending one packet. In 1 second, how many packets you are sending? 1 upon 2 TP plus TT, which is packets per second. So basically, this is also throughput. This is also throughput. This is also throughput. Both are throughput. Basically, it is just in bytes per second. It is in the packets per second. Let me know, have you understood the meaning of the throughput? Okay. So Kanak is saying, because like Kanak is answering to Shobhadeep, he's saying that at the TP time, sender is not sending anything and just sitting idle, waiting for the ACK. Okay. So yeah, so basically, like, I mean, in stop and wait, what we do? We just, in stop and wait, we just send a packet. So basically, there is one packet that's going to take TT time to just transmit. So I'm just writing that vertical line means it is basically time window. Okay. So this time is TT time, and then it is going to receive a packet after 2 TP, right? So this time is basically 2 TP, and then completely, I say completely, it is 2 TP plus TT. That's the time that I have in my hand in the stop and wait, right? I transmit something, then I get something. So are you clear with this notation? I mean, this diagram, time diagram. So here I'm just writing the time. Okay, TT time, transmission time. So that's why I'm writing it like that. And then this, from here to this is the moment, then your packet is completely transmitted, and then from here till you get the ACK, it is 2 TP, right? This is the time that you have in your hand, but sender is just busy for here. Sender is doing something. Sender is just busy here only. In all other time, it's waiting, right? This is, sender is ideal. Sender is sitting idle, right? Okay, cool. Now throughput is clear and efficiency clear, right? Great. Now we are very set to do any of the question with related to the stop and wait, and also with related to the sliding window also. Let me know if these terminologies are clear, because these are very, very confusing to most of the students. Now Now let me quickly revise it using the slides only, okay, and then we will directly go to the questions. See, in these many seconds you are sending L bytes, so there's the throughput which is in the bytes per second. Similarly, you can also find the throughput in the packets per second. In these many seconds you are sending one packet, so that's why this is 1 upon 2 TP plus TT packets per second. That's the throughput. Now let's just go to the two formulas that we have derived. One was the throughput and another one is efficiency, right? I mean, throughput we have in terms of bytes per second. This is the throughput, which is bytes per second. Now efficiency we have we have derived three formulas, which is like number of packets we can send, total packets we can send, number of packets we are sending with respect to time, with respect to bytes also, right? I mean, this is, one second, this is the bytes we are sending and the bytes we could have sent, right? The numerator is bytes we are sending, L bytes we are sending, bytes we could have sent is basically into bandwidth, and I'm just taking it bandwidth outside. So these are the three formulas which we have derived for the efficiency. This is the formula that we have derived for the throughput, and also for the throughput we have derived, which is 1 upon 2 TP plus TT packets per second, right? Packets per second. I mean, either you write bytes per second, packets per second, there will be a difference of L because the unit is different. Cool. Now let's just check if these two formulas, which is throughput and the efficiency, let's just call this efficiency as sigma, is eta, and are these two formulas are related? Can you just check whether this efficiency, which is this formula, and the throughput, which is this formula, are these related? Yeah, these are very much related, and you will say that these are related by the bandwidth. So you can, if you multiply by the bandwidth in the efficiency, you will be getting the throughput, right? You will be getting the throughput, which will be in the bytes per second. That's okay because there has no unit. There's a no unit, and this is bytes per second. Okay, that's why the throughput will be in the bytes per second. Cool. Have you understood everything? How we are calculating throughput, how we are calculating efficiency, and everything is set, right? Okay, now let's do the questions. Now, before the questions, maybe I can also tell you about the sliding window, which is selective repeat and go back end, right? I mean, the formulas and everything remains same. It is just a little one thing will get changed. So the concepts are same. So it is just going to take 1 minute only. Sliding window protocol. Here, instead of sending one packet, what we do, we send the packets of size window, right? We send the complete window, which is called sender window. Okay, sender window size. So instead of sending just one packet, we send WS packet. So that's why we just have 2 TP plus TT time in our hand. Okay, this is the time in our hand. Now earlier we were sending one packet, now we will be sending that many packet. So now can you tell me the efficiency here? Efficiency will be how much packets you are sending, how much packets you could have sent. You could have sent, I think 1 plus 2, right? 1 plus 2 is the packet that we could have sent. So that's the efficiency. Now, what will the throughput? Throughput is basically, throughput will be number of bytes we are sending, right? So how many bytes we are sending? Maybe you can say WS into L. I mean, obviously, like if these many packets you are sending, then into L, these many bytes you are sending. And how much bytes you could have sent? Sorry, how many bytes you are sending upon the total time, in how much time you are sending, basically 2 TP plus TT. So this is the throughput. Now, if you just check both of this, I mean, again, the formula will be remain same. Throughput will be bandwidth into efficiency. Now, currently you might say that I'm just, writing it directly, or I'm just teaching it too fast. So let's do one thing. Let's just go to the question. You will realize that whatever you already know will be just applicable to the question very, very naturally. I mean, you do not have to do much of the things there. Okay. So let's just continue with the questions directly, and then you will be able to relate whatever we have just seen is directly applicable to the questions. And as I said, like questions will be from the gate only. Like we will be focusing gate PYQs in these sessions. So in the marathons, 1 or 2 questions I probably will be taking from the standard universities that are not from the gate, but mostly we will be focusing gate questions. Okay. So let's just start the questions. Now, what we are saying, a channel has a bit rate of 4 kbps and one way propagation delay of 20 millisecond. So, the propagation delay is given to you, okay, which is 20 millisecond, and a bit rate is given in the kbps, it means it is a bandwidth, right? So, bandwidth is given to you, which is 4k means 10 is power 3 bits per second, okay, it is bits per second. The channel uses stop and wait protocol. The transmission time of the acknowledgement frame is negligible. To get the channel efficiency of at least, so efficiency should be greater than equal to 1 by 2. Okay, 50%, the minimum frame size should be. So they are asking about the frame size. Okay, see, that is very good if you know the formula, which is 1 upon 1 plus 2a, right? If you know the formula, that is very good. But I mean, it is up to you again. I will say that you do not remember the formula. Okay, what you need to do, let's just do the practice without remembering the formula. Three, four questions we will do without remembering the formula. Then you will see that you do not actually need to remember the formula, and you can handle more complicated questions if you do not remember the formula. Okay, so I'm not going to apply 1 upon 1 plus 2a, that is the efficiency formula for stop and wait. I'm not going to apply it. Why? Because I just want to see if I can do it without using the formula, without just having some fundamentals with me, right? Okay. So this is the propagation time, this is the bandwidth. Whenever these two are given, and by seeing these two, there should be the transmission delay also given. So let's suppose the transmission delay is TT only. Okay, so by seeing these three, I should be able to find out what is the number of bytes we can send. Okay, number of bytes we can send. Or maybe if you want to find out the efficiency, like you can do it any terms in the sense you can see with respect to time, you can see with respect to the bytes, you can see with respect to the packets. So let me know what you want. Should we go with respect to time? Let's just go with respect to time. Okay, let's just make a rule that always we are going with respect to time. So how much time we are utilizing in stop and wait? This much only. How much time we are having in the hand is this much, right? 2TP. This is the efficiency. Now you will say that I have written the formula, that is we already know. I mean, why you are disallowing me to write 1 upon 1 plus 2 or whatever we know directly, because this is same, right? Whatever I have written, it is same as 1 upon 1 plus 2a. But let's just make a habit of writing with respect to time, efficiency with respect to time. Reason being is that you will be very much comfortable after some time. I mean, if you do it, then you will be comfortable in very complicated questions also. Okay, write the efficiency with respect to time. It should be greater than or equal to 1 by 2. Then let me just write it here. I mean, it is given to us that should be greater than or equal to 1 by 2. Then it should be T2TT plus TT plus 2TP. Then TT is greater than or equal to 2TP. Then TT is basically length upon bandwidth. So length, that implies length should be greater than or equal to length upon bandwidth should be greater than or equal to 2 into TP into bandwidth. So let's just go to the next page. I mean, this is just a calculation. Probably you can do it, or maybe I can also do it. Let me know if this efficiency formula, that whatever we have written, the way we are going is fine to everyone or not. Okay, so the L is going to be this. The way we have written is basically with respect to time I wanted to write it. I mean, you can apply 1 upon 1 plus 2a, but why we are not applying is basically if the question is complicated, they insert you many things. I mean, they say queuing delay, processing delay, whatever, right? Then you can come up with those solutions very easily if you are using the intuition. Okay. So now this TP is going to be 2 into what is the propagation time that is given to us? It is 20 milliseconds into bandwidth is in the seconds, right? So I need to convert that into a millisecond. So 4 into 10 to the power 3 bits per second. So per second means if I convert that second into millisecond, then I need to multiply by 10 to the power 3. So here 10 to the power 3. So finally this it will be in the bits. So length, this will be in the bits. So 10 to the power 3, 10 to the power 3 is cancelling out. Then this is 160 bits. Length should be greater than or equal to, greater than or equal to. Minimum length should be this much. Okay. Is this fine to everyone? So minimum length, if they are asking, it should be, length should be greater than or equal to 160. So minimum length should be basically 160, right? Actually, stop and wait is preferring a longer frame. See, stop and wait, like if you want to increase the efficiency in stop and wait, there is only one way. You cannot increase number of frames, right? In stop and wait, the number of frames are fixed, which is just one. So if you want to increase the efficiency in stop and wait, then what is the, what is the best thing to do? Can anyone tell me? If you want to increase the efficiency, since you cannot increase the length, then so you cannot increase the number of packets, then what is the best thing? Just increase the length, isn't it? It is best if you increase the length. So that's why I will say, let's just increase the length, which means if I am just sending one packet, let's just send more bytes. That's the only way to increase the efficiency in the stop and wait. Okay. So I hope you understood. So that's why they are saying that if you want to have efficiency of, efficiency which is actually 50%, then you need to have length which is greater than or equal to 160. Yes, Alok, that is right. Increase the packet size or decrease the bandwidth? No, decreasing the bandwidth can increase the efficiency. I mean, you are not optimistic then. I mean, why will if the formula is saying even the decrease the bandwidth, then even though if it is saying by the formula wise, then that kind of efficiency I don't want, right? I mean, you are saying that you are making my resources very limited, you are making my bandwidth very congested, and then you are saying you are efficient. No, I'm not efficient. I just made it worse. I mean, I'm okay to have higher bandwidth and not efficient, okay, rather than okay to have a lesser bandwidth and being efficient. So what's the point of that efficiency, that I'm decreasing my resources? Okay. So anyway, so I hope you understood. So basically, since I'm just sending one packet, that's why it is better to send a longer packet. That's the only way. Cool. Now let's just move to the next question. Okay, they have also used the efficiency with respect to time, but it is up to you. I mean, how you are going to solve the question. But I will say, don't use the formula, use the intuition, because that's how you can solve the more questions very easily. Okay, so let's solve this question. This question has been asked in GATE 2006, and what they are asking is, let's see. So they are saying on a wireless link, the probability of the packet error is 0.2, which means a packet is having an error is 0.2 probability, right? So probability of error is 0.2. A stop and wait protocol is used to transfer the data across the link. Okay, so they are using stop and wait protocol. The channel condition is assumed to be independent of the transmission to transmission. What is the average number of transmission attempt required to transfer 100 packets? So what they are saying, that if you are sending a packet, then this packet may be an erroneous packet. It may get, it may be having an error that is having a probability of 0.2, which means with the probability of 0.2, the package will not be reaching successfully. Even if it reaches successfully, the receiver will discard, right? So probability that a packet not reaching successfully is actually 0.2. In other words, probability of success is 0.8, right? Probability of success is 0.8. Success means that reaching a packet is reaching successfully. That's what I mean by success. Okay. Yeah. So now let's just see how to solve this question. See, they are saying the probability of success is 0.8. Now, can you tell me how many number of trials? Okay, let's just forget that this is the question from computer networks. Just tell me this is a question from probability. Let's suppose this is a probability question. So just tell me number of trials we need to get a success. That is equal to, can anyone tell me? It should be 1 upon probability, right? 1 upon probability of success. How to get it? I hope you know it. If you do not know it, then you can see my probability lecture probably. There I have told you that how to get it. Or maybe I can tell you quickly. Okay. See, if I'm just telling you quickly that we have already discussed in the probability lectures, if the probability of success, let's suppose probability of head is, let's suppose P. Okay. Which means you are tossing a coin, the probability it will come head is P, probability it will come tail is 1 minus P. Now, I'm asking what is the expected number of tosses to get a head. That is what? then you will say that probability of head is P, then the answer is going to be 1 upon P. And how? That's what I'm going to tell you. Okay. So you have a coin, with you. You are going to toss a coin, whether it will be head or it will be tail. Now tell me, if it is a head, then won't you stop? You will stop because you want a head, right? Expected number of tosses to get a head. So you want a head in your experiment, you will stop. So till now you just did one toss, and you will say that if you get a head, then it's just one toss. If you get a tail, then what are the number of tosses you will need? See, with this probability you will get a head, and with 1 minus p probability you will get a tail. If you get a head, then this is the expected number of tosses that is there. This is just one. Now, if you get a tail, then what is the expected number of tosses? Let's suppose expected number of tosses to get a head is just E, right? So if you get a tail, then you need to restart everything because there is no point in the toss. You need to restart everything. So restart means that you are going to spend, if earlier it was E answer, you are going to spend E as an now answer also. So basically that if E is the expected number of tosses that you need, so with P probability you will need one toss, with 1 minus P probability you will be needing E tosses. So that's how you can calculate this E. If you calculate this E, it is going to be 1 upon P. See, I have taken a 3 hours of lecture just to tell this completely in the probability lecture. So I know it might not be very convincing at this moment because I just told you in 3 minutes or maybe in lesser than 3 minutes. But it is a long topic where we have done many questions. So you remember one thing. You do not need to know all of this. You remember one thing, which is that if probability of a success is P, then expected number of trials to get the success is 1 upon P. Similarly, if probability of success is 0.8, then expected number of packets that you need or expected number of trials to get the success is 1 upon P. So basically, if you are sending one packet, then the probability of success is 0.8. Then my question is that how many packets you need to send till you get a success, right? So till you get success means here success was head, here the success is sending a packet. So how many packets you need to send? Just to send one packet is 0.8. So just to send one packet, you need to send 1 upon 0.8 packets. Now they are saying 100 packets you need to send. So into 100. So if you do it, then I think it will be, so yeah, I think it should be 125, right? 125 is the answer. Let me know if there is any confusion or you have got everything. Okay. Let's just continue. See, I have also commented on the gate overflow almost the same thing, which is this. Right? You can also read this comment later. Now let's do one question which I have taken from MIT. So there is one question that I have taken from MIT, and the reason why I am doing this question and not the gate PYQ, because this question is very much related to one of the gate PYQ that we have. Now that PYQ is going to be very conceptual. That's why let's just first practice with one of the question from where that PYQ is actually copied. Like I don't know like they have copied it or not, but yeah, that is very similar to the PYQ that we are going to do in just a couple of minutes. Okay. So let's just see this question. Before that, let me know how you are liking the session. If you want anything to accommodate in this session, then we are very much open to your feedback. If you want me to take only PYQs, then also that is fine. I mean, I will just take 1 or 2 questions from different universities if that is relevant. Otherwise, we will be just taking the PYQs. Or there is any other suggestion that you want. If there is everything you are liking, then I just request you to like the session so that we get more reachability over the YouTube, because that's how the YouTube algorithm will work. So just like this session and just spread this word among your friends so that they can also get benefited and we can also get benefited. Okay, so let's just continue. Now what they're saying, this question I have taken from MIT, and there is no need to say that MIT is top-notch university of this world. MIT, Stanford, Caltech, these universities are obviously top-notch universities. Berkeley, MIT, Stanford, And there are many others, obviously, like Berkeley University is a favorite university for me and Deepak. Like most of the questions we take from Berkeley University because their assignments are very good. And Caltech University, and then University of Buffalo, UMSD. So there are many universities from that we take questions generally. Okay. So what they are saying, consider two hosts A and B. Suppose the network path from A to B has a bandwidth of 5 kb per second and a propagation time of 120 millisecond. So what they're saying that now just listen this question carefully, because this question is same as the next PYQ that we are having. So in this PYQ that has been asked in grade 2016, this PYQ and the question that we are currently going to solve from the MIT, these two questions are almost same. So why they are same? Because here in this PYQ they are saying the sender is sending this much, and yeah, size of the acknowledgement and the transmission rate is this. Okay, I think that PYQ is after it, so not this PYQ, maybe the after it PYQ. But yeah, but let's just solve this question and then you will get to know that why I am saying it. Okay. So see, consider two nodes A and B. Suppose the network path from A to B has a bandwidth. So they have given a different bandwidth from A to B and B to A. That's why this question is little interesting. Not just little, it is very interesting. So also, like I will say that I am going to put this kind of question in All India Mock 2. So like I'm very much interested in putting that question in All India Mock 2, some version of this where I will be having two different bandwidths from A to B and B to A. So they are having two different bandwidths from A to B and B to A. So from A to B they are saying that 5 kb per ps is the bandwidth, and the path in the reverse direction from B to A has a bandwidth of 10 kbps. So they are having two different bandwidths here. That's why this question is very, very interesting. Okay, cool. Now let's just continue. Now what they are saying is that, and a propagation time of 120 milliseconds. So from A to B, the propagation time is given to be 120 milliseconds, and the reverse direction. So here the propagation time from A to B, TP, that is given to us, that is from A to B is given to us is 120 milliseconds, and from here the propagation time from B to A is also given to us, which is 80 milliseconds. Right, the path in the reverse direction, and that is okay. Let data packets have a size including all headers of 500 bytes and acknowledgement packet of the size. So the size of the data is also given, which is 500 bytes, and size of the acknowledgement is also given. Length of the acknowledgement is also given, which is how many bytes? 100 bytes. Now what they are saying, give a numerical expression for the throughput that A can achieve in transmitting to B using stop and wait. You can treat a 500 byte packet as transmitting 500 bytes of useful data, that is ignore it's a bit due to the headers. Okay, so basically they are saying that this is the setup, and then they are asking about the throughput that A can achieve in transmitting to B. So that's the question. So let me just copy this question and the data that they have given. Okay, so let's just remove everything else. So they have given this data, and then they're asking about the throughput. Now let's just if you are very clear about the fundamentals, then you should be able to do this question very easily. Let's just see what is the time in your hand that you have. Time in your hand. Let's just first attack on the basic, right? Because from here only I am driving everything. From here only we are going to drive everything. Time in your hand means total round trip time. So round trip time basically. You will send a packet, right? You will send a packet, which means it is going to take propagation time plus propagation time, which is this one, plus the transmission time of the packet, right? So let me just write propagation time for the packet plus transmission time for the packet plus propagation time and transmission time for the ACK, because this is the time. Do you remember this time? I will recall you, don't worry. So this is for ACK, this is also for ACK. This is the total time that you have. What is this time? or this time? What is this time? This is the time that you have, from the moment you start the transmission till the packet is reached. Till the, packet is reached. From the moment you start the transmission till the packet is reached. So TP plus TT. So let me just recall you what is this time. See here. TP plus TT we have already written. Yeah. So time any packet takes from very start of the transmission to other host get it completely, right? So this is the time. TP plus TP is very important time, which is the time that you start the transmission till it get it completely. So that's the TP plus TT. See, this is the time is the time for the from the moment they start the transmission till the first packet is reached completely, or the any packet completely reached to the receiver. Completely reached means that you do not need to worry about whether you are the first bit is reached or last bit is reached. So you send any packet, this is the time that it is going to take totally, right? Okay. Now let's just continue. So basically this is the time that you have in your hand. Then can you calculate this totally? This TP, I think it is given to us. This is 120 milliseconds, right? Because this way propagation delay is 120 milliseconds. This way is length is given to us. Length is given to us, which is data length, and the bandwidth is also given to us, which is 5 kb. So let me first find out this time, right? Let me just find out the transmission time for the packet and the transmission time for the ACK. So these two times let me first find out, right? And then I will use those in the next formula. So transmission time for the packet will be length of the data, which is 500 bytes, upon how much time you are going to take, which is 5 kilobytes per second. Bandwidth. So 5 kilobytes means 5 into 10 power 3. Bytes are matching. I do not need to worry about it. This will be in the second. The whole will be in the second. That's why into millisecond it will be this, right? So I think 100 millisecond. Similarly, time for the ACK. Let's just find out this, right? Let's just find out this quantity also. Let me know if you are fine with this calculation or not. So this is going to be length. What is the length? 100 upon bandwidth is 10. So 10 kbps. K means 10 is power 3. It is in the seconds, then milliseconds it will be this, then it will be 10 milliseconds. So this is coming out to be 100, this is coming out to be 100, this is coming out to be 10. Okay. The propagation delay in this direction is given to us is what? The propagation delay is 80 millisecond. Okay. So this is 80 millisecond. 80 millisecond plus this is coming out to be 10. This is the total, which is going to be 210 milliseconds. Let me know if this is fine to everyone or not. This is 200. Sorry, this is 200 and this 300. So this is 310. Yeah, not 210. This is going to be 310. So see, like once you find out, once you attack on the fundamentals, then these questions will be very easy. Now you know that this is the time that you have in your hand. Now whatever they are asking should be very easy to you, right? Now let's just see what they're asking. So now time you have in your hand is 310 milliseconds, right? So maybe I can just for now, maybe I can just remove this. So the total time, let me write it, RTT is 310 milliseconds. Now what they're asking is throughput. What is throughput? Throughput is basically that how many bytes you are sending in 1 second. See, in stop and wait, what you are doing? You are just sending one packet. In 310 milliseconds, you are sending how many bytes? You are sending one packet of 500 bytes, right? 500 bytes. You are just sending 500 bytes. So you will say 500 bytes you are sending in 310 milliseconds, which means in 1 millisecond. Okay, you will be sending 500 upon 310. This will be bytes per millisecond. If you actually want in the seconds, you can just convert that to, since it is millisecond, you can convert it to 500 upon 310 into 10 to the power 3 bytes per second. So it will be 1000. So it will be 2. So it is somewhere around 1 upon 620 bytes per second. So this will be your throughput. Let me know if that is fine to everyone. See, you can also find the throughput using the formulas and all, but trust me, it is going to be too much of cumbersome. Okay. So just a second. This is fine, right? In these milliseconds, you are sending 500 bytes. So in 1 millisecond, you are sending 500 upon 310. So this is bytes per millisecond, and then you will be multiplying by 10 to the power 3. Okay, so this will be 10 to the power minus 3, not 3. Sorry. Yeah. So this will be 10 to the power minus 3. So now it is going to be 500 into 10 to the power 3 and then divided by 310. Right? So let me see the answer. 500 divided by 310 milliseconds, which is actually, I mean, you can calculate it. This is 1613 bytes per second. You can check 1613 bytes per second. Now, I dare you to find it using the formula. Okay, so you are going to use bandwidth into throughput. Sorry, what they're asking, throughput, right? You are going to use maybe efficiency into bandwidth or whatever, right? So this is the formula that you are going to use. Throughput equal to efficiency into bandwidth. Now you need to find the efficiency first. Okay, that itself, I mean, it will take unnecessary time, and then you will be getting confused that which bandwidth to use, because there are two bandwidths, A to B and B to A. Actually, you want to find the throughput at A, so that's why you should be using the bandwidth at A only. But still, you will be getting some confusions. So basically, you just attack on the fundamentals. Once you attack on the fundamentals, then things will be very, very easy. Okay, I hope you understood this question. That's the same question that they have asked in one of the GATE PYQ. That's why I have solved this question upfront. Yeah, Swapnil is saying almost similar question in one of the test series. I tried bandwidth into efficiency and it never got solved. Yes, like that's what I'm saying. I dare you to solve using the formula. I mean, honestly, you can solve it. There is no problem. I can show you that how to solve it. Okay, but okay, let's just do one thing. Let's just do the GATE PYQ, and in the GATE PYQ, I will show you that how to solve it. Okay, but actually, it is a waste of time. That's why we should not do it. But you can definitely do it again. Okay. Cool. Let's just solve the GATE PYQs. Maybe I'm just skipping other questions because if you want, you can do it as an homework, because like I just want to focus on the GATE PYQs. Okay. So I mean, there are 3-4 parts, but I'm skipping other parts. These are other parts are actually comparatively easy. Maybe they are asking some other questions which are comparatively easy, but the question that I wanted to focus on is the throughput. Okay. Cool. Let's just do this question. Now, see, that's why I'm again saying just okay, just attack on the fundamentals. Just whatever you are doing, just do it with the fundamentals. If you are doing with the fundamentals, then definitely you should be able to solve questions very, very easily. I mean, there should not be any issue while solving the questions if you are doing with the fundamentals, which means just know what is the efficiency, what is the throughput. Throughput means that is something that is measuring that how many bytes I can send in the second. Maybe they can ask you how many packets you can send in a second. So it depends on the unit. Efficiency means with respect to time, it means that how much time I am utilizing divided by how much is the total time, like that, right? Just focus on the meaning of that term, and then you should be able to solve all of these questions very naturally. Okay. Now let's try this question. Okay, so Pradeep is saying rote learning is like, okay, now ठीक है मैं चलता हूँ. Yeah, it is always like the case with the Go classes. Cool. So what this question is saying, a sender uses the stop and wait ARQ protocol for the reliable transmission of the frames. Frames are of size 1000 bytes and the transmission rate is this much that is given to us. So they are saying reliable transmission of the frames. Frames are of size 1000 bytes. So the length is given to us, which is 1000. And the transmission rate at the sender is, so the transmission rate at the sender, which means the bandwidth is given to us at the sender. And at the receiver, see, there are, yeah, this is the same question. There are two different bandwidths, which means at the sender, they are saying the transmission rate or the bandwidth is given to us, which is 80 kilobits per second, okay, per second. And from B to A, they have given the another bandwidth, which is given to us 8 kilobits per second. Size of the acknowledgement is 100 bytes and the transmission rate. Okay, the size of the acknowledgement is also given, which is the 100 bytes. Oh, I think this is the same question or this is the different question. I won't be surprised if they have directly copied it. Is this the same question? No, this is 5 and okay, this is 5, 10, 500 and 100. Okay, I mean like this is 100 times this is 10 times this, almost the similar numbers, right? I mean, they have not given the propagation, I think, but yeah, apart from the propagation, the numbers are almost similar. I mean, this is 8. Okay, the bandwidth is 8 and the length. Anyway, let's just continue it. The size of the ACK is also given. One-way propagation delay is 100 millisecond. They have given the one-way propagation delay. Maybe the propagation delay in both the directions are same. That's why they have just told you in one of the way it is 100 millisecond. So the TP is given to us is 100. Now they are asking about the throughput. Okay, so TP is given to us is 100. Now just find out the total time in the hand that you have. Okay, total time in hand. Total time they are spending. How much total time you are spending? You will send a packet. A packet send means TP plus TT, right? You will send an ACK, that is TP plus TT again, ACK for the ACK, right? That's all. So for the packet, what is the total time that you are taking? Let me go to the next page. So for the packet, how much total time you are taking? You are saying that, is this visible? Okay, you are saying maybe sorry about it. Let me just also remove this. It is TP, the transmission time. What is the transmission time? This is 1000 upon bandwidth. Bandwidth is 80 kilo means 10 to the power 3 bits per second. Okay, it is in bytes. Since it is in bytes, let me convert that to bits. Now the whole quantity is in the seconds. That's fine. Plus the transmission time. This is okay. This is the transmission time. The propagation time. Propagation time is 100. 100 is in second or what? It is in millisecond. Okay, so that's why let me convert that also to a millisecond, which is 10 to the power 3. Okay. Then for the ACK, what is the length? Length is 100 bytes. That's why you need to multiply by 8. It is in bits. Now divide by bandwidth. It is 8 into k, 10 to the power 3. This is bits. This is also in bits. Then it is in second, but I need milliseconds. So that's why this is in the millisecond. And then finally, the propagation time for the ACK. So that's the total time that you have. So that will get cancelled out. That will get cancelled out. 8 will get cancelled out. This 8, this 0, 0, 8 will get cancelled out. This is 100 plus, this is basically 100 plus 100 plus 100 plus 100. So this is 400. 400 milliseconds, that's what you have total in your hand. Now, in this 400 millisecond, what they're asking is throughput, right? So in this 400 millisecond, or maybe you can write it other way, basically you need bytes per second. So basically you are sending 1000 bytes, right? 1000 bytes in 400 milliseconds, or maybe write in that way, in 400 milliseconds. Actually this is unitary method, and in childhood only I from that days only I remember that if they are asking, let's suppose if they are asking in 1 millisecond what you can do, okay, then you need to write the millisecond or the second thing on the left part. If they are asking in the 1 second millisecond, if they are asking in 1 byte can be sent in how much seconds, something like that, then you need to write the byte on the left hand side. Okay, so anyway, like I know that you know this is very basic. So in 400 millisecond, you are sending 1000 bytes. You are sending 1000 bytes. So they are asking that in 1 millisecond, you will be sending 1000. So throughput is 1000 bytes per 400 milliseconds. Right. Now let's just see the unit that they have. They are having bytes per second. So let's just convert it to bytes per second. This is millisecond. So you can convert it by multiplying 10 to the power minus 3, which means you can convert by multiplying 10 to the power 3 in the numerator. 400 into 10 to the power 3. This is bytes per second. So this is 2 zeros will get cancelled out, or maybe that Yeah, so basically this 4 will be dividing it by 25 times, 25 0, and then this 0 0 get cancelled out, this 0 will be this 0, so 2500 bytes per 2500 bytes per second should be the throughput. Let's see the answer. Yeah, 2500 bytes per second. So let's see what method they have used. Okay, the total time, yeah, they have also used a similar method. But you do not need to, I mean, you do not need to worry about it, because we are going to use the same method. We are just you're going to use the fundamentals in all the questions, not in just this question. Okay, in all the questions we are going to use the same fundamentals. Okay, cool. So let's just continue. Let me know if you are getting the things. If there is any doubt, you can also let me know. Let's just see this question. Okay, and let me see how many other questions that I have. Okay, there are a few more questions that I have that we can actually solve. But there is one video that I already have on our channel, where I have solved most of these questions. Maybe you can watch that video. Okay, because if I solve all the questions, then I might not be able to move to the other topic. So is it okay if I move to the other topic, because all of these questions can be solved using the fundamental that we have. So just do one thing, like let me just move to the other topic. Okay, so see whatever question that we have, or maybe I can solve one or two more questions. Let's just solve this question, and then solve the remaining questions using the fundamentals that I told you. Okay, so let me just solve this more question, and then we will be moving to the different topic. Cool. So what they are saying is this: suppose the stop and wait protocol is used on a link with a bit rate of 64 kilobits per second. Okay, so they are using bandwidth of 64 kilobits, 64 kilobits per second, and 20 millisecond is the propagation delay. So bandwidth is given to us is this, and propagation delay is 20 millisecond. Assume the transmission time for the acknowledgement and the processing nodes are negligible. Okay, the minimum frame size in the bytes to achieve the link utilization. Okay, so they are saying the link utilization, which is efficiency, should be at least 1 by 2. Now, which means in terms of time, it is this 2 TT plus TP. Sorry, 2 TP plus TT, right? So TP is given to us. I think this is almost the same question that we already did. So from here you can find out that this should be greater than or equal to 1 by 2. Then this is 2 TT is greater than or equal to 2 TP plus TT, right? I hope you are getting. So this is TT is greater than or equal to 2 TP, and TT means length upon bandwidth. So length should be greater than or equal to 2 TP into bandwidth. So assume, I think this is the only question that they are asking. Suppose it's a stop and wait protocol is used, bit rate of this second and the propagation delay is also given to us. Yeah. So can you just do it? What is the TP? TP is 20 milliseconds. Okay. So let me just remove all of this. So TP is 20 milliseconds. 2 into 20 into bandwidth is 64K kilo, right? So what I want in the bytes. Okay, so let me just convert that to bytes. This is bits, so this is bytes, and then this is second, but it is in millisecond. So maybe I can convert that second to millisecond, which means I need to divide by 10 to the power 3. So this will get cancelled out. This is 8 into 2, like 8 into 4 will be 320, 64 into 320 bytes. Okay, so let's just see the answer. 320 bytes. I think we did some calculation mistake. Is this? 2TP plus TT, this should be greater than or equal to 1 by 2. Okay, what they did, this is propagation time, transmission time, 2TP plus TT. Yeah, 2T, this is just 2TP plus TT. So 2TP plus TT is coming out to be 40 plus x upon 64 milliseconds for them. Okay. These many bytes you can send. Amount of data that could be sent is this. Now that is fine. However, they are calculating. I mean, okay. 2TP. You are saying this already in bits. Okay. Yeah, bandwidth. This is already in bits. Now are you getting 320 here? We are still not getting 320, right? There is one more factor of 8. Got it. So basically, this is in this is in the bits. See, this finally 2 into TP. TP is 20 and 64 kilo bits per second. So it is in the bits. Yeah, we need to convert that into byte, right? The minimum frame size in the bytes to achieve that rate. Oh, this is in the bits and we need to convert that to a byte. And for that, I need to divide by 8, not multiply by 8. Sorry. Yeah. So I need to divide by 8 and then this will be 320 bytes. Okay. So, I mean, all of the questions that whatever you are doing can be solved using the fundamental only. Just recall your fundamental that how to solve those questions and then you should be able to solve these questions, right? So let me know that if things are fine. If there is any difficulty, then also you can let me know. Yeah, I divided by 8. I divided by 8 and finally we got the answer. Cool. Now let's just continue, and for the next topic we are going to see some networking devices, right? Now, which means we are going to see what is hub, what is router and these things, and then we will be solving the questions based on that. Okay. So here there is one popular protocol. Do you remember there is something called spanning tree protocol? Spanning tree protocol. So we are going to see this spanning tree protocol also. Now, do you want to continue in the same session or should I schedule a next session? Let me know quickly. Do you want to continue the same session or should we have a break of 30 minutes and then we can continue another session? It is up to you, however you decide. I'm fine with everything. Okay. So, okay, should we continue? Cool. Maybe maybe I just need a break of 5 minutes. So let's just have a break of 5 minutes, okay? Then after 5 minutes, okay, let's meet at after 10 minutes, okay? Meet at 12, and then we will see the spanning tree protocol. The topics we are going to discuss, topics we will be discussing is spanning tree protocol, learning bridges, collision domain, broadcast domain, like that, right? So these kind of topics we are going to discuss. So let's meet at 12:10. I hope that is fine to everyone. Hi all, I hope you can hear me. Sorry for a little delay. So let's get started. So first of all, let me know if you are enjoying the sessions or there is something that I need to accommodate. Okay, Soumik is having one doubt. I have a doubt in the previous lecture. If RTT is mentioned, then what is your doubt? Then while calculating the efficiency, should we use this transmission time upon RTT? Okay, so that's very nice doubt. So let me just copy this doubt here. Okay, so Soumik is asking this doubt. Actually, this is one of the common confusion that many of the aspirants are having. That I mean, they use some formula which is TT upon. First of all, RTT is well defined, and in most of the cases, RTT is the whole time. I mean, the whole time that is including the TP and the TT. I mean, this is called RTT as per the Wikipedia, but sometimes some people use as just 2 TP. I mean, as per the Wikipedia, it is the total time in the sense that that whatever time that you have from the moment you start the transmission till you get the ACK, which means that if you are having the processing delay, if you are having the queuing delay, everything is just RTT. That's what they say. But anyway, let's not go with this definition. So basically, if you are using the formula, then there is a confusion that should we be using this formula or should we be using this formula, right? I mean, should we be not adding TT or should we be adding TT? So that's one of the common confusion that most of the aspirants have. Answer of this question is basically, okay, sorry, that video is hiding the thing. So I hope now you can see this, right? Now, answer of this question is basically it is little bit ambiguous in the sense that it depends also on author to author. Like I mean, in the sense that if you see, I can just paste the link in the description also. If you see, there is one question at the MIT University itself, and then in that question they have given the answer using the both formulas. They have said like if you use this formula, then this is the answer. If you use this formula, then this is the answer. Which means that if you add TT, if you do not add TT, then they have accepted both the answers. So there is a thing that I will say that this is more precise. To be honest, I will say this is more precise, but it is also dependent on the author. Okay, which means these two formulas are author dependent. I can tell you that if you look at the frozen, okay, I will send you a link of the gate. I mean this Go test series question where I answer that question, and I have put the reference of all. So there is one MIT PDF that accepted answer in both formulas. I mean, they have explicitly mentioned that either you use this formula or you use this formula. I mean, we have accepted both the answers because it's not well defined like that. I mean, to be honest, this is more precise. This is more precise. But yeah, there is one MIT PDF. I can send you some frozen page number, okay, frozen book reference book. They have not used. I mean, they have not added one, which means I mean if you use 1 upon 1 plus 2a, they have did it I mean instead of it they have added it, they have not added 1, which means they are just using this, which means they are using this basically. And similarly, I can send you one reference from Tenenbaum book. They are using 1 upon 1 plus 2 okay, and they are not using this. I mean they are not using 1 upon 2. They are adding actually 1. They are not using 1 upon 2a. They are using 1 plus 2a. Here they are using 1 upon 2a, and there is one MIT PDF that says that you can use either of them. So that's why it is a little bit not clear, to be honest. Okay. So it must be clear from the from the options that what is their intention. But you should be using this one if you just want to use the formula. You should be using this one because it is more precise. But all of these links, all of these reference, I can send you. You can just comment over this video. Okay, just let me know if you really want the reference. I will send you the reference. All of these links. Okay, I will tell you the frozen page number. I will tell you the tandem page number. I will send you the MIT link also. I will send you all of these links. Just comment after the video is the session is over. Comment as a usual comment, not in the live comments. Okay, and then I will reply to your comment with the reference. Okay, so Joy is saying, can GATE math teacher solve J? Okay, sir, I have a doubt on a previous lecture. Okay, that's fine. Is it possible to apply the strength and reduction? So Vivek, like, I mean, what you are asking even, like, please, this is computer networks class, you are asking compiler design questions. So, because in case of calculating token ring protocol efficiency, no, it's not like that. I mean, it depends on what is their intention. So, it should be clear from the options. Okay. So, okay, let me just continue. Will GATE people be mentioning? Yeah, they should mention it. I mean, they should give the options in such a way it should not be a conflict. Cool. By the way, this RTT is also, let's see, the CN subject is a little bit ambiguous, I will say. I mean, not every time they define all of the things. But yeah, if you look at the RTT definition also, see, let me just go over the Wikipedia page. Yeah. So from the Wikipedia, they have said that RTT is including everything. They are saying that this is round trip time is the amount of time it takes a signal to be sent plus the amount of time takes for the acknowledgement of that signal having been received. So send and receive the acknowledgement, right? They are taking the both of the things plus the amount of time the acknowledgement has been received, right? Which means in between whatever is having is actually RTT. Okay. So, I mean, like in the CN, some of the things are a bit ambiguous. I completely agree because this is a very practical subject in the sense that most of the applications are just a practical applications, and that's why the people. I mean, it is depending on the question that whether the options are having 1+2A or 2A. So that's why the people have not set much standard about some of the things. So every time there is some dispute about the CN questions that happens in most of the time. Cool. So now let's just continue. Let's just continue with the networking devices. So which means we will be seeing some of the networking devices and some of these things. So let's see this question, what this question is asking, and then maybe we can take the motivation from this question to study the networking devices. So they are saying which of the following is false regarding a bridge. First of all, we should be knowing what is a bridge, okay? And then they are asking about something about the collision domain, broadcast domain, and these things. So we should be knowing what is a bridge, and then only we can talk about these things, right? So that's why let's just first see the theory. So similarly, this question has been asked based on something called a learning bridge or the transparent bridge. Okay, these are also called learning bridges, right? So for that we should be knowing what is the transparent bridge. So that's why I mean similarly this question also that they have asked, this question is related to the number of subnets that they are asking, and this question has been asked very recently in GATE 2022. So maybe you can see this question clearly now, right? So they have asked this question, and for that you should be knowing things very clearly that how to calculate the number of subnets and all. So that's why like let's just take a motivation from these 2-3 questions and let's just see the topic that I want to discuss, which is networking devices, right? Okay. So see here we have different layer and there are different devices that we have at every layer. What do I mean by that every layer? It means that these devices, the hub or the repeater or bridge or the switch or the router, these devices work on that layer, which means these devices can see the packets up to that layer, the headers up to that layer. Which means if I'm using repeater or hub, then they cannot see the data link layer header or the network layer header like that, right? Okay. Now let's just first see the repeater. What is a repeater? Suppose that these are the two hosts and in between I sit like I ask a repeater to sit. So this is a repeater. Now how does this behave and what it is actually doing? Let's just understand this. If these two hosts are connected, then this repeater is first of all is very dumb device. Very dumb device work at physical layer only, works at physical layer. So what do I mean by that? See here, this repeater is basically working at the physical layer, repeater and hub. So what do you mean by that? That it cannot see any packet, it just modify the signal, which means whatever bits and bytes you are having here, then if the signal is not too much strengthened, then it will just restore the signal. So it just restore the signal. As you can see, it is like I like the way this picture is showing is basically it just amplify the signal, right? This is an amplifier, a voice amplifier that generally we use, generally to announce something we use these kind of amplifiers, right? So this is basically just amplifies signal and doesn't do anything else. That's all. This is what repeater do. Okay. And then what is a hub? Okay, suppose that these are the few devices or these are the few hosts that you have with you, and what you want to basically connect all of these hosts to each other. Then what you can do, you can use multiple devices. There are multiple options. One of the option is that you can use hub. Hub is a option that can connect multiple devices at the physical layer, which means that you can use the router also, you can use the other devices also, that's fine, but you can at the minimal you can use the hub. So if I say that what to put here to connect all of this, then you will be saying that you can put a hub here, right? So you can put a hub which can connect multiple devices, and hubs are simply multiple repeaters, which means there is no difference between hub and repeater. These are just two terms. Generally repeater have only two ports, but hubs have more ports than the repeaters. Okay. And also there is not very standard way that I can say that hubs are having more ports than the repeaters. I mean, see, whenever we say this is few, this is less, this is more, this is high, then it is with respect to what, right? I mean, is this few or this is more for you? These four ports that is having, then you will be calling it repeater or hub. So that's a question. I mean, these are the very not well defined things, which means like you can say that hub and repeater are actually same. But yeah, if that is having too many ports, then you will say it is hub, like that, right? So you like for our purpose, we will say hub and repeater both are same. There is no difference between hub and repeater. Okay, so we will say that hub and repeater are actually same. There is no difference between hub and repeater. Now let's just see. Okay, Devadut is asking that can hub regenerate signals like repeater? Yes, it can definitely do it, right? So that's the purpose of this hub. So hub can definitely regenerate. Okay. So let me know if there is any other doubt. Now, hub and repeater are both are same. It is just simply multi-port repeaters. Hub is a number of input lines that is joined electrically. Frames arriving on one line send to all others. And if two frames are at the same time, they will collide. Okay. Cool. Now see, this hub is also very dumb device, just like a repeater. So basically they works on physical layer, which means it doesn't know that where to forward, which means if some packet is coming, let's suppose from A and it wants to go to B, okay, some packet that A is sending to B, then it doesn't know that I should send to only B, it will send to C and D also. So if A wants to send to B, if there is a hub always and always broadcast, it doesn't know. I mean, not only if A is sending to B, it will not only send to C, it will also send to D, right? It always broadcast because it is very dumb device. It doesn't know what to do with the incoming packet, where to forward. Okay. See here, everyone receives everyone else data. That's what the hub do. Everyone receives everyone else data, right? Cool. I hope you understood. Now let's just see the other devices. So what is a bridge here now? See, there are two devices that we have just seen, hub and repeater. Both are actually same. Now let's just see bridge and switches. So suppose that this is one hub that you have. This is also one hub that you have. If you want to connect two hub connected host, then generally we use the bridge. Okay, bridges only have two ports generally. Again, this is generally. They can also have multiple ports. So bridges learn which hosts are on each side. Yeah, that is very nice point that I will tell you that how it learns. Even if you have attempted our test series, then I think one or two questions I have put based on the learning bridges. Okay. Anyway, we will see this. So is this clear that bridge is going to connect two hub connected devices generally? And what is the difference between bridge and hub? Bridge are little smarter, which means bridges works on works on data link layer. Okay, which means that bridges can read the data link layer frame. How? Let me just show you. So before that, I will just put a definition of switch, and then we will see the difference between bridge and the switch, right? So cool. Now, what is a switch? Switch is basically connecting, just like a bridge. It is also connecting multiple hosts, and you can connect to hub. To hub connected devices also using the bridge, using the switch. So basically, switch is just like a multi-port hub, multiple bridge. Okay, switch is a combination of hubs and bridges. It is for our purpose. We will keep it very simple. Switch is just multi-port multi-port bridge. Now, since it is multiple bridge, every functionality is same, just with the number of ports are higher. But again, this is very subjective, that how many ports should be there in the switch and how many ports should be there in the bridge. So that's why, like, I will say that these are actually same. I mean, there is no standard definition that separate both of them. So switch and bridge are same for our purpose. It is just generally, it is just multi-port. Similarly, hub and repeaters are same. Generally, hubs are multi-port. Okay. Now, I will say this is working on data link layer. This is working with voltages, which means at physical layer. Okay. Otherwise, switch and bridge are same, hubs and repeaters are same. Now, let's just continue. So suppose this is a switch which is connected to different hosts, and this is one network. So the network name is 192.168.1 dot something. So if it is dot 11, this is the host, dot 44, this is the host, like that, right? Okay. So switch basically does not separate the network. We will see the router which actually separates the network. But if you are connecting using switch, that host on the network share the same IP address space, which means there is one network. If you are connecting with the switch, you will call it one network. If you are connecting it using the router, I will tell you, okay, then you will say that, okay, it is actually creating different networks. So I will tell you in a moment. Before that, let's just see that how to how basically these switches are learning. Just a second. Yeah. So let's just see that how these switches are learning. Let me tell you that learning bridges or learning switches. Learning bridges. Bridge and switch both are same. Okay. You can call it learning switches. Does not matter. So both are actually same. Now let me take this example and let me show you that what they learn and how they learn. So suppose that this is one network that we have, okay, and in this network there are different hosts that we have. Maybe let me not bothered about their IP address because it does not matter for the switch. Okay, so let me just name these as different hosts, maybe A, B, C, D, E. Okay, maybe let me just call it A, let me call it B, let me call it C, let me call it P, Q, R. Now let's just see that how learning bridges are actually working. Because they have not asked any question till now from the learning bridges, but if we just spend 5 or 10 minutes, then maybe there's a chance that if they ask, then we can easily answer that question. That is easy score question. So how they learn is very simple. Suppose that as a first step, okay, first packet, that A sends. So initially switch does not have any table, that is called switch table. Okay, just like a router table, they don't, let's suppose this is the port number 1, port number 2, like that, right? So they do not have any table. The table is empty. Okay, this is an empty table initially. This is switch or the bridge table, just like a router table. Okay, so if A sends a packet to P, then what will happen? This packet will go to this switch. Tell me, does initially this switch knows that where to forward this, where is P on this port? Let's suppose this port numbers are 1, 2, 3. Okay, maybe you can say this is the port number 1, port number 2, port number 3, and this is 4, 5, 6. Tell me, does this switch knows that that packet should be forwarded to P? I mean, packet should be forwarded to only just one port initially, because the table is empty, right? So since the initially table is empty, it does not know. So what this packet will do? I mean, what this switch will do? It will just broadcast to every other port, which means it will broadcast to 2, it will broadcast to 3, it will broadcast to 4, 5, 6. So if A sends a packet to P, then switch broadcast to everyone, because initially it does not know. And this is the first packet, right? This is the first packet. Now, interestingly, this switch will learn something from this first package. What it will learn is basically, it will say that, okay, based on the source, what is the source? Source is A, right? Now it will get to know that, okay, based on the source, it will get to know that, okay, A is on this side of the port. It will get to know that A is on the port number 1. Isn't it? How it is getting to know? Because based on the source, it builds the switch table. Based on the source, it builds right, which means it will say that, okay, now A is on the port number 1. Now let's see very interesting point. Now suppose as a second packet, if let's suppose P or maybe Q, okay, let's suppose Q wants to send to A. Q sends to A. Now what will happen using this packet? Tell me, let's suppose if I ask you a MSQ, okay, if I ask you a MSQ where I say the first packet, okay, suppose there is an MSQ. This question is, let's take it as MSQ. Okay, suppose first packet sent is from A to P. Now Q wants to send to A. Then which of the following host receives that packet? Okay, so options are, first option is, let's suppose Q wants to send to A, then maybe let me call it B, E, call it A, B, C. So what is the correct answer? What are the correct answer if this is MSQ? Let me know. What are the correct answers? P. If the first packet is sent from A to P, then it means this switch will now get to know, based on the sources get to know, right? It will get to know that age on the side that is port number 1, right? Now whenever someone is sending to A, now it knows, now the packet is coming to A, now it knows that where is A. Now it will only send to A, it will not send to anyone else. So that's the difference, right? Now only A will receive this packet. So because that's how it has learned that A is on this side, and now it will also learn that Q is on port number 5, right? Q is on the port number 5. So that's how the things are working. Yes. Yeah, so that is fine. So Tadika Dappa Akash. Yeah, so A is the answer. Shobhadeep, A is the answer. Pratik, A is the answer. Yes. So A is the answer, right? Okay. Now let's take one more question immediately, and then let's suppose this is a hub. Okay. Suppose A, B, C are connected to a hub. Now suppose there is a switch, there is one more hub. Let's suppose P, Q are connected to this hub. Suppose that first packet sent is from A to R. Second packet is sent from Q to C. And now if if let's suppose R sends to then which all will receive. Now, if R sends to A, then which all will receive? Let me know quickly. Let's have options. Let's suppose this is MSQ. Okay, so this is A, B, C, P. Let me know. If R is sending to A, then see, this switch will get to know, because of the first packet, the switch will get to know that A is on the port number 1, right? A is on the port number 1. R is sending to A to R. So A to R, so switch will get to know A is on the port number 1. And then it will get to know that Q is on the port number 2. Although this is not useful information for the question, but yeah, that's fine, right? It will get to know that after these two packets, it will get to know that A is in the port number 1 and Q is in the port number 2, isn't it? Now, if someone is sending to A, then it will not send to not send again first of all to this P and all, right? I mean, the switch will not send because this is the incoming packet, but because of this hub will send to everyone. So P and Q, this hub will send to this P and Q. So that's why the P will receive, but the switch will send to only this this hub, but this hub will send to everyone. That's why everyone else will also receive. That's the problem. Now P will also receive, right? P will also receive because of the hub, and then again because of this hub, B and C will also receive, because hub is a dumb entity. So if that question has been asked, then you will say all of them are correct option. Okay, I hope now you understood. That's called learning bridges. Very easy, right? Now let me tell you one concept which is called collision domain. Okay, so let me tell you one of the concept which is called collision domain, and then we will see one of the concept which is called broadcast domain. Okay, so as the name suggests, it is a domain. Domain means it is a set of something, right? So basically the definition is that it is a set of node or host in which if any two hosts are sending data simultaneously, then there will be a collision. So what do I mean by that? Let me just tell you. See, let's suppose this is what I have. Okay, let me just copy this. Let's suppose this is not a switch, this is a hub. Okay, just for the example, let's suppose this is a hub. Consider that this is a hub, and these are the nodes that I have, or the host that I have. This is A, this is B, this is C. Let's suppose this is P, Q, R. If someone is sending to something, okay, so collision domain is a set of nodes where if one of them is sending to some other, okay, which means it will say that A, let's suppose I say this is a collision domain, then what do I mean by that? I say that if this is a collision domain, only if A is sending to P or A is sending to C, then and some other node are also sending, which means B and P are also sending at the same time. Like I mean, there are two communications, which means there is a communication between this pair, there is a communication between this pair. Then there will definitely be a collision. That set of nodes is called collision domain. See, it is a set of nodes or hosts in which any two hosts are sending data simultaneously. Okay, I mean, let's suppose that A is sending the data and C is also sending the data. Any two hosts, you pick any two. If they are sending the data simultaneously, then there will definitely be a collision. Why? Because C is sending the data, then this hub will do what? Hub will send to this channel also, and A is also sending the data. So that's why there will be a collision. If you pick any two nodes, if they are sending the data simultaneously, there will be a collision. That's why all of this is in collision domain, right? Okay. Now let's just see one other example where instead of this hub, I do have a switch, and let's suppose the switch has learned, which means that it has learned that where the hosts are. Okay, I mean ABC is on which port and PQR is on which port. Now, if there is a switch which is already established, I mean it has its own switch table, which is all of the entries are fine there. Now, if I just ask you whether all of this will form a collision domain or not, then you will say if you are saying that this is a collision domain, okay, if you are saying that this is a collision domain, which means this A, B, C, P, Q, R, then what does this mean? If A is sending to, let's suppose some data, A is sending some data, this is A, B, C, P, Q, R, okay, A, B, C, PQR. If A is sending some data and at the same time, if P is also sending some data, then will there definitely be a collision? That's the question. If P is also sending some data, then will there definitely be a collision? See, if P is sending to A, then yes, there will be a collision. But if P is sending to, let's suppose someone else, if P is sending to Q and A is sending to B, then will there be a collision? Will this switch forward the packet that is coming from A to this line also? No, right? I mean, this will just not forward, this will just deal with this will just deal with this. I mean, that's not necessary that there will be a collision. There can be the collision if A and P both are sending to each other. Otherwise, there is no necessity. So since there is no necessity, that's why this is not a collision domain. Collision domain is a set in which if any of the two hosts are sending data simultaneously, then there will be a collision, right? There will definitely be a collision if any of the two hosts are sending data simultaneously. But if since not and not, there is no certainty that there will be definitely a collision, that's why that particular set of nodes are not forming a collision domain. Okay, so I hope you understood this. Now, what is happening here? This, if we are having this switch, then this switch is basically dividing the collision domain, or you can say reducing the collision domain, which means one port, whatever it is connected to, that port will be having the same collision domain, which means, let me just tell you the example. So here, if you are having a switch and let's suppose this is A, this is B, this is C, this is P, Q, R. Now the collision domain is saying that if you are even, okay, let's suppose you are saying AP is in the collision domain, then is this true? If A is sending a data and P is also sending the data, let's suppose to R or something, and A is also sending the data, then will there be definitely collision? No, not necessary, right? I mean, if A is sending to P, only then there will be a collision, otherwise there is no collision. So if A is sending a data and P is also sending a data, then there is no collision, so that's why you will not say it is a collision domain. So basically, switch reduces the collision domain. So every port of the switch is one collision domain, right? So basically only A is one collision domain, only P is one collision domain, only B is one collision domain, like that. Like, let me just simplify this. For example, let's just take this example. So suppose that I do have this kind of configuration where I'm saying that there is a switch that is connected to a hub which is connected to some host. Now, can I say that ABC is in one collision domain? Can I say? Tell me. If A is sending to anyone and B is sending to anyone, will there be definitely a collision? If A is sending to anyone and B send to anyone, then there will be a collision. Why? Because if A is sending to anyone, hub will do what? Hub will send it to B. And if B is sending to someone, then definitely there will be a collision. So yes, I can say ABC is one collision domain, right? So I will say this is one collision domain. Okay, Akash is asking, if A is sending to B and P is sending to C, will there be any collision domain? No, collision domain is fixed, which is, I mean, see, once you say that this is a collision domain, if you are saying A and P is a collision domain, then A can send to anyone and P can send to anyone. You need to show that there will definitely be a collision in every case. You let A send to anyone, you let P send to anyone, there will be definitely a collision in every case. Tell me, if A and P are in one set, then there will be definitely collision in every case? No. Right? A can definitely send to anyone and P can definitely send to R, and in this case there is no collision, right? So if you're putting them in one set, then there must be a collision in every case. There will be a collision, wherever they are sending, right? That's what a collision domain means. Okay. So I hope that is clear. So which means, like, if you're putting that in one set, then you ask this particular element, this particular host to send to anyone, this particular host to send to anyone, there will definitely be the collision in every case. That's why this is called a collision domain. They are forming a collision domain. Okay. Now, so now you can say that ABC is in one collision domain because A is sending to anyone and B is sending, you pick any one of them or any two of them. If A is sending to anyone, C is sending to anyone, then there will definitely be a collision. Because A is sending to anyone, then this hub will send to B and C also. And if B or C is also sending to someone, then there will definitely a collision, right? Now, this is one collision domain. Similarly, you will say that PQR is one collision domain. PQR is another collision domain. So now you will say that these are the two collision domains. So switch basically separates the collision domain. It is one collision domain. It is one collision domain, right? Similarly, earlier also, this every of this node is in one collision domain. Okay. Now, tell me, can I say that ABCPQR is this whole is in one collision domain? Can I say that ABCPQR, this whole thing is in one collision domain? You pick two. You pick two. Will there be definitely a collision? Suppose A is contacting B and P is contacting R, then this switch will not be having any collision, right? And that will say, okay, you just transfer to P or to C, and the P will transfer to R, right? So there will not be, like, this is not necessary that there will be a collision. So that's why you will say that this is not a collision domain, not a collision domain. But earlier you had a collision domain, right? So you will say that this is one collision domain. Okay. I hope that is clear. This whole hub is basically forming one collision domain. Hub always form the entirely as one collision domain. But switch separates the collision domain or reduces the collision domain. Right. Now let's see one of the term which is called broadcast domain. Okay. These are the two terms that we have, and once you have this understanding, then we can solve the questions related to these terms and also related to the networking devices. Then we will see the spanning tree protocol also. Okay. So what is the broadcast domain? Can anyone tell me what is the broadcast domain? See, again, as the name suggests, it is a set of nodes, right? Yes, Subhadeep, that is correct. ABC and PQR are two collision domain. Yes, that is correct. So see, it is a set of nodes in which if one host broadcast, then everyone else receives the packet. Okay. So which means you will say that this is a broadcast domain. Let's suppose you are saying that ABC is a broadcast domain. ABCD is a broadcast domain. Then it means that you are saying if A broadcast, then everyone else should be receiving. Then this forms a broadcast domain. Okay. So here we say ABC ABCD is a broadcast domain if and only if one of the, okay, any one of the node from the set broadcast the packet. If any one of the node from the set broadcast the packet, then everyone else receive it. Okay, so that's called broadcast domain. Now let's just check what are the broadcast domain here. Tell me, can I say that all of this is in one broadcast domain? If A is broadcasting, then see, this switch is basically for the broadcast. It will since this is a switch and router just drop the broadcast packets, and the broadcasting is generally done at the network layer, and router basically stop the broadcast, but switch does not stop the broadcast. So if A is broadcasting, then who will receive the packet? Everyone will receive, right? So that's why this will call a broadcast domain. So everyone including A, B, C, P, Q, R, this will form a broadcast domain. So we will talk about the router in a second, broadcast domain. And then router basically stop the broadcast. Now probably this is the right time to go to some of the basic questions that I started with earlier. Now tell me, which of the following statement is false regarding a bridge? They are asking about the false statement. Bridge is a layer 2 device. Yes, it is a layer 2 device. It reduces the collision domain. Does it reduces? Bridge or switches both are the same thing. Tell me, does it reduces the collision domain? Yes, right? It reduces the collision domain. So that's why you will say it is also true. It is also true. And then bridge is used to connect two or more LAN segments. What is a LAN? See, LAN is just local area network. Local area network. Which means some of the hosts are getting connected, then it is called LAN. I mean, few nodes connected, that is called LAN. There is something called WAN, which is wide area network. Wide area network. This is basically internet. Okay, WAN means internet. Internet means you are connecting many devices. I mean, again, this is subjective, that you will say, is this WAN or this is LAN? Because if you are connecting many devices, almost all the devices of this universe, then it is called internet. I mean, all the devices means everyone who wants to connect to the internet. If they have connected to the internet, and you are connected to basically a large set of devices, then it is called internet or WAN. If you are connected to very small set of devices, it is called LAN. Okay. I mean, internet is just a bunch of router put together. Internet is basically a bunch of router put together. Okay. So LAN is basically some small number of hosts you are connecting, and then yes, bridge can be used. Bridge is used to connect two or more LAN segments. So basically, it is called extended bridge or extended LAN. I mean, this C is called extended LAN. So basically, like I will tell you in the spanning tree protocol. I mean, a spanning tree protocol generally used with the extended LAN only. So this is some LAN. Okay, LAN means some group, okay? Some host connected to each other, right? Similarly, I mean, how they are connected, it will depend. Maybe they are connected using bridge only, maybe they are connected using hub only, right? So there are some hosts that are connected to each other. Similarly, there are some other hosts which are connected to each other, which are forming a LAN. Then what you can do, you can connect these two LANs using a bridge. Using a bridge, you can connect these two LANs, and that is called extended LAN. Okay, this whole thing is called extended LAN. So yeah, it is used to connect two or more LAN segments. So that's also true. Bridge reduces the broadcast domain. That's false, right? That's false. So that's why D is the correct answer if they are asking about the false. Yeah. Okay. Now, maybe let's do this question. Which of the following is not true with respect to the learning bridges and router? Both bridge and router selectively force data packet. I think they do, right? So yeah, that is true. They are asking about the not true. I mean, router has its routing table and bridge has its own bridge table. A bridge uses IP address while the router, okay, that is not true, obviously, right? That is false. A bridge builds up routing table by inspecting the incoming packet. Yeah, that's very nice point. And then if you have understood the learning bridges, then only you can do it. Routing table or the bridge table, whatever you want to call. Okay, routing is basically sending a packet is called routing. A router is a device and routing is different. Okay, everyone does the routing. I mean, at the end you are just doing the routing. So everyone does the routing. So you call it routing table. That's not a wrong thing. So yeah, that's also true. It actually builds up its routing table or the bridge table by inspecting the incoming packet. A router can connect a LAN and WAN. Yeah, definitely it can connect. Okay. I mean, LAN is just a small set of hosts, and that is actually not just can connect, it is actually used to connect that thing. I mean, you have some small host, which is your mobile, your laptop, and there is a router that you have that actually connects to the internet, right? And that is also called default gateway. I mean, gateway or the default gateway. Gateway means this is the first router that you reach to in the internet. That's called default gateway. I mean, that is connected to internet, and this is the first device that you are reaching to go to the internet. Okay, this is internet, and that's called gateway. Or I mean, router. This is also router, but just some terminology which is called gateway. So that's also true. Good. Now, before solving this question, maybe let's just see the router and then we will solve that question. So what is a router? Okay, let's just see a router now. A router facilitates the communication between the network. So basically, if you want to connect two networks, then you can say that you can connect using a router. So basically, there is one network that is connected by a switch. I mean, there is a bunch of hosts that is connected by a switch. There is another bunch of hosts that is connected by a switch. And if you are connecting them, you can connect using a switch again, but let's suppose you are connecting them using a router, then this router is, let's suppose, connected to the internet. So basically, if you're connecting them using a router, then this actually divides that network. So you will say this is some sub network or maybe network 1. Okay, you will say this is another network which is network 2. So these are not the two networks, and that router is also connected to internet. So for example, see, there is one router and this is connected to 3 networks, 1, 2, 3, right? Now each router is basically having some interfaces. Let me just tell you what do I mean by that. This is a router and this is connected to, let's suppose, one LAN. Okay, this is internet. Let's suppose this is one LAN, some small set of host. Let's suppose this is some LAN. This is also some. Since I put the router, there will be 3 different networks. I mean, one network for this, network 1, and now what will happen, this network is having some couple of IP addresses with us, right? I mean, let's suppose this is /25 or /30 or whatever, right? Let's suppose it is /25. Then it will be having some couple of IP addresses. Can you tell me what is the first address? I mean, first address, not numerically, but just like conceptually, the first address, you say it is a network address, right? Network address. Can you tell me what is the last address for any network? It is basically, can anyone tell me? It is broadcast address, right? Broadcast. Okay. Now you just remove the first and last address. Whatever the IP addresses it has the complete authority of. I mean, this network has a complete ownership on those IP addresses. So it will give some IP addresses to its host, and then it also give some one of the IP address to this interface using this network. Okay. From this network, one of the IP address will be given to this interface. Which IP address? Generally, the second one. Okay, generally the second one. The second IP address is from the start or maybe from the last, generally, but it is not compulsion. Okay, you will be giving one IP address to the net from this network. Okay, one IP address here. Similarly, from this network, you will be giving one IP address. Similarly, from this network, you will be giving one IP address to this interface. Similarly, there is a network here, and from there also, you will be giving one IP address here. Okay, so there is a question that has been asked in GATE 2022, which is number of subnets, right? They have asked the number of subnets. Now, if you want to count the number of subnets, let's suppose they give you that this, and they ask you that what are the number of subnets here, right? How many subnets are here? Then you will say that it is just the interfaces that you have. How many interfaces you have? This is 1, 2, 3. I mean, you just divide this using the interface. So basically, you will say that this is one network. I mean, it is connected to one network here. It is connected to one network here. It is connected to one network here. 1, 2, 3, and then this is also connected to one network, 4. And since these interfaces are common, you do not need to count them twice. Okay, just count them once. So this is one. I mean, whatever the red color, one internet, one network, two subnet, three subnet, 4. I mean, every interface is one network, right? Every interface. This 4, 5, and then 6. How many are they? Answer is 6, right? This diagram I have taken from Cross. That is given there. This was the question when most of the students were not able to answer that question. Even unfortunately, I mean, that's always the case, but yeah, unfortunately, most of the institutes have also put that answer wrong in their answer sheet. Only on the GATEOverflow, we were able to give the correct answer, because that's how the GATEOverflow works, right? So on GATEOverflow, I answered it, and I was 100% sure, because that was the basic question. So everyone was opposing that answer, and they were just I mean, just having their own answers. But at the end, Gate accepted our answer. Okay. So now if I ask you how many subnets are there, no, you will say 1, 2, 3, right? Now 3 subnets are there. Right? So there are the 3 subnets, the figure by Crucian rows. Now let's just answer this question, and then we will move to the learning the spanning tree protocol. Okay, just a second. Yeah. Can you see this question clearly? Okay, maybe let me just tell you the drawings. So the drawings might not be 100% clear here. So this is one line. Okay. Similarly, this is one line. This is another drawing. Now they are asking about the number of subnets inside this enterprise. Now how many subnets are present? How many subnets are present? Sumant is saying the learning bridges reduces the broadcast domain. No, broadcast means that you need to broadcast to everyone. Okay. Only broadcast always means that in which network. Broadcast is defined for the network. In which network you are broadcasting. Switch is basically not connecting to different networks. It is within the network. So it broadcasts to everyone within the network, because that's the job of the switch or the bridge, right? But router stops the broadcasting, because broadcasting is always made for only one network. You cannot broadcast to every network in the internet, right? That's why the router drops the broadcast packet. Okay, so answer is 6. Why? Because this is one router, this is one interface, this is another interface. This is 1 2 3 4 5 1 1 2 3 4 5. Yeah, this is 5, right? 1 2 3 4 5. Okay, what is the counting here? The drawing clear? So this is 1, right? This is one interface, second interface of this router, third interface, fourth interface, 5 interface, and then this is 6. Yeah. So these are the 6, right? Do not count any interface twice. If a router is router connector, do not count it twice. So answer is 6. I hope you understood, right? That was an easy question, but yeah, nice question. So 6 is answer. Okay. Now let's move to one of the concept, which is called spanning tree protocol. So let's just quickly do that, and then we will be moving to the error detection also. So that's how we will be completing this particular topic of the data link layer. Okay. So there has been one question that has been asking GATE 2006, which is this question. Now it is up to you. Let me quickly know, should I cover this topic, because they have just asked one question from this topic. Let me quickly know, should I cover this spanning tree protocol or not? Because they have just asked only one question from this topic. That's why I'm asking. Okay. Let me know. Should I be covering it? Okay, let's just get the overview quickly. Cool. Let's just do it. So let's first quickly do it. This spanning tree protocol. Then we will be moving to two concepts. Two methods of the error control, which is Hamming distance and the CRC. And the way we are going to do it, not just a usual approach. We are going to dig deep. We are going to see that how the Hamming distance and CRC actually works. Before that, let's just cover this topic, which is spanning tree protocol. It is actually very nice topic, but since they have not asked the question, that's why I was just asking you whether should we cover it or not. But yeah, if everyone wants, let's just do it. So before that, some representation I want to tell you that how the networks look like. So this is one representation. Representation means that I will give you some diagram. I will say that this is a LAN. LAN is just a group of hosts. Okay. Then I will say that this is a LAN, and I will represent this using a cloud. I will say this is a LAN, this is another LAN, and these two LANs are connected using some bridge. These two LANs are connected using some bridge. So this representation clear to everyone. Okay. So we are having some LANs which I will represent using a cloud. Using a cloud. This is just one representation. I can represent something like this also, which means I can say instead of the cloud, I can say I can give you the details, which means I can say that in this lane, what are the all hosts that are there? Okay, in this lane, like currently this is just one host, but yeah, these are the different hosts. So instead of the cloud, I can just open up the bubble and I can tell you that exactly these are the hosts that are there in this line. But I hope this representation is also fine. So instead of the cloud, I can just give you the more finer details. Finally, I may skip the cloud, I may skip the host that is connected to this line. I will just say this is one line. Okay, I will say A is one line, V is one line. So instead of the cloud, I will be having a straight line. Okay, all of these straight lines are a line. Straight lines is a line. Okay, so this is just one another representation, and then I can say instead of maybe like instead of telling you that okay, that what are the details, I mean inside this cloud, I think this is the same as that I earlier had. So I will not be telling you the details, I will be just saying that these are the lanes and these are the bridges. Okay, let's suppose these are the bridges. So this is just the same representation that I earlier had, or bridges or switches. Okay, or maybe I can say that I can even skip the cloud representation also. I can say that okay, this switch is connected to this switch, maybe directly or maybe via some line. Okay, maybe they can also connect directly, I mean that's also allowed. If they're connecting directly, that's also allowed, that's not a problem. So anyway, like I will be representing the line via cloud or maybe via a straight line. That's the only thing that I want to convey. I hope that is fine to everyone. Cool. So this is a graph. In the graph sense, it looks like this, which means these are the host and or these are the lines. Let me call this A, B, C. These are all the lines. In between, in this B, there must be multiple. There might be multiple hosts. Let's not worry about it. So what is the problem here is that suppose there is some packet that someone is transferring. Okay, some let's suppose A is sending a packet to someone. Then what may so happen that this packet may get into the loop. See here, this is a loop that before may send because of some error or maybe intentionally, unintentionally, it can be in the loop. And because of multiple packets in the loop, then there will be a congestion. And suppose that we are only using that communication only at data link layer. There is no network layer protocol. So here at the data link layer, they do not have any access to TTL, right? Even if there is a network layer protocol, they do not have any access to TTL. They do not have access to TTL field, right? For the routers, we have the TTL, but for the bridges, they cannot see the IP header, so that's why they do not have access to the TTL. Now, how to solve this problem? Which means how to prevent the looping? What do you say? So the core idea is that we will prevent the looping. How? We will say that okay, let's just do one thing. Let's just remove some of the ports virtually. Virtually means like conceptually I will remove. I will say that okay, let's never use this port. Okay, let's suppose let's say I'm saying that let's never use this port. Let's just remove these two connections. If I remove these two connections, then I think this is a tree. This is a tree, right? So the idea is to remove conceptually some connections such that finally we get a tree. So that's the final aim, that we get a spanning tree here, right? Is this final aim clear to everyone? That's the final aim. So what we want finally, we want a tree. How we are wanting a tree? I will say that okay, let's not use this connection, maybe let's not use this connection, and how to determine that which port to use, which port not to use, that is done by the spanning tree protocol. Because we do not have any access to the TTL, that's why we need to do all of this story. Okay, let's just continue this. I hope the objective is clear. What is the objective? Given any topology, I want to disconnect virtually, I mean conceptually I want to do it, I want to block some of the ports such that finally I get a spanning tree. Okay, so we want to block some of the ports so that finally we get a spanning tree. A spanning tree means it has all the nodes, but it is a tree. That's the objective. Okay. So there are few definitions. Before I go to the algorithm, let me quickly tell you few definitions. There is something that is called root bridge. There is something that is called root port. There is something called designated bridge and designated port. Okay. I mean, actually these two terms are same. I mean, these two are same. There is no difference in these two, but yeah, just the terms are there. So that's why I have written it. But yeah, these two are same actually. I mean, and this is very easy. I mean, this is very straightforward, and you only need to find out these two: root port and designated bridge or designated port. So let's just see that what are these terms and what are these doing. So what is a root bridge? Okay, let's suppose this is a topology that is given to me. Then the first step, let me tell you step by step. Okay, so step one, which is very easy. Step one, that basically says that determine root bridge. It is very easy. The bridge which is having the lowest number is called root bridge. So here, can you tell me immediately what is a root bridge? B1 is a root bridge, right? So I will say this is a root. Very easy. Now let's go to the step 2. It says that for every bridge, determine root port. So what is a root port? And we need to do it for every bridge. What is a root port? A port which is closest to the root bridge. Okay, a root port is actually a port for each bridge, the port that is having minimum cost to the root bridge. So basically, can you now tell me that what is the root port for B3? Is this, let's suppose this is 1, this is 2. Which one is the root port for B3? Which port is closer to the root? That's called root port. Which port is closer to the root? I think it's very easy to answer. And what is that? 2, right? Port number 2. So port number 2 is closer to B1. So that's why you will say this port is a root port for B3. Similarly, can you find the root port for B4? Okay, or maybe let's just do it for B2. Yeah, like, I mean, there are two ports. Let's suppose this is port number 1, port number 2. Which port is a root port? I think 2, right? 2 is directly, I mean, this is one line, I'm not considering a line. 2 is directly connected, and 1 is connected via B4 and then by B3, then it's connected to B1. No, I don't want it, right? So this port, 1 is root port for B2. Now similarly, I can say for B2, this one is root port. Similarly for B3, this one is root port. Similarly for B4, this one is root port. So B3, B2, B3 are like these one root port. And now can you find out the root port for B5? Is this the root port? No. Is this the root port? This is connected to B4, then this is connected to B4. It's connected to maybe B2, and B4, B2 are coming in between, and for this only B3 is coming in the between. So I think this is the root port, right? So I will say this is the root port. Very easy to find out the root port also. Now you are done. I mean, that's all we needed to do. So you find out the root port, and then the last step, which is also very, very easy. Actually, this algorithm is very easy. Step 3, it is called finding the designated port for each LAN. Okay, find or determine the designated. Okay, designated means designated port, DESI. For each bridge. That is all. Now, for each lane, I need to find out the designated port. Now, what is a designated port? Have you understood the root port? Now let's just see what is a designated port. See, that's very easy to find out the designated port. The designated port is the port of the or the designated bridge. Actually, both are the same. Okay. So designated, we need to what for each line we need to do it. For each line we need to find out the designated bridge or the designated port. What we need to do for each line, the bridge that provides the minimum cost, the bridge that is closest to the root bridge, that is called designated bridge. Okay. For example, let's say for A, which one is the designated port? First of all, we need to find that which one is the designated bridge. Designated bridge is a bridge that is closest to this line. Which bridge is closest to the line? Just B1. I mean, which bridge is closest to the to this line such that it has the closest distance to the root. Okay. If this line wants to go to this root, then which path it will be taking? This one, right? So this is the designated bridge. For A, B1 is a designated bridge. For G, B1 is a designated bridge. For B, B1 is a designated bridge. See, for A, B1 is a designated bridge. For B, B1 is a designated bridge. For G, B1 is a designated bridge. And designated port is just a port that is connected to the designated bridge. Okay. So that's why I said like these two are same. So basically, finding the designated bridge is also very easy. This line will say for each line we need to do it. This for A, I will say what is the closest bridge. Okay, that will using which using which bridge I can reach to the root in very less time. So since they are directly connected, this is a designated bridge. That's why this is a designated port. And G is directly connected to to B1. That's why this is the bridge which is a designated bridge, and that's why this is a designated port. Similarly for B. Now, what are the lines that are remaining? C, F, E, and D. These are the four lines that are remaining. For those, we need to find out the designated bridge, right? For C, what do you think? Which is the designated bridge? C will go to B4 or B3 to reach to B1. Tell me. C will go to B4. C has three options: B3, B4, or B5 to reach to B1. Which one it will choose? Definitely B3, right? So that's why for C, the designated bridge is B3. That's why this is the designated port, right? Okay. So I will revise it. Don't worry. But I hope you are understanding. We will just see it once more. Don't worry if there is any confusion, right? Okay, so this is the designated port. For D, tell me what are the options. I think for D there is only one option, so that's why there is no confusion for D. Okay, for D there is no confusion. For F and E, let's just find out the designated bridge. For F, which one is the designated bridge? I think B2. B2 is closer to this B1, right? So for F, this is the designated bridge. And for E, E have I think one or two options. Which one you choose? B4 or B5? I think B4 is closer than B5, right? B5, okay. B5 is also closer. B5 will be basically having one hop away. B5, B3, B1. B4 will be also B4 and then B3, B1 or maybe B2, B1, whatever, right? So both are at equal distance. For E, since both are at equal distance, either it choose B4 or choose B5 because both of them are equal distance at B1. So it will choose with the minimum ID. That's why it is choosing with the B4. Now for F, there are two options, either B2 or B4. Which one it will choose? It will choose which is having the closer to B1. So B2 is closer to B1. That's why it will choose this one, B2, right? So that's why this is the designated port. That's how easily you can find out the designated bridge and designated port. So should I go through it again? Very easy. Okay, these steps are very easy. Let me just once you do it, then the algorithm is actually done. So our idea is to block some of the ports, and we need to finally come up with the spanning tree. Okay, that was our idea. Now what we need to do, there are three steps. I mean, step one is very straightforward, determining the root bridge, right? So root bridge is the bridge with the lowest ID. Step 2 is basically determining the root port. Step 3 is basically determining the designated port. For each bridge you need to do it, and step 3 is for each line. Step 3 is for each line determine designated bridge. Okay, for each line you need to determine the designated bridge. That's all. So let's first determine for each bridge. For each bridge, which one will be the port? Root port, this one, right? And that's how you can easily determine. And then for step 3, let's just determine designated bridge for each line. Let me just say designated bridge. Let's just determine designated bridge for each line. So whenever you have couple of options, you will say whichever is closer to the root. Okay. So I think this step is also very easy. So finally, we come up with this. Now we are done with our root port, we are done with our designated port. Whatever the remaining ports that you have, see, this is neither the root port nor the designated port. That's why I will remove this. I will remove this. So whatever the remaining ports you have, just remove them or just block them. See, root and designated ports are forwarding state. Other ports are in the blocking state. You just block them. That's all. Yes, Somik. We will see that for every bridge or for every line, which one is closer to B1. Right? Okay. So now can you do one thing? Can you just remove this and then see if finally what we are getting? Let me just do it. So this is what you have, right? And let's see if we are getting a spanning tree or not. And this is after the removal. If we remove these two, isn't it a spanning tree? Isn't it a tree? Do you see any loop here now? There is no loop, right? So you will say it is a spanning tree. If you just draw the spanning tree using the bridges, then you can say that this B1 is root, and then B1 is connected to B3, B1 is connected to B2, so B3, B2, B2 is connected to B4, B3 is connected to B5, right? So that's how you are having a spanning, right? That is very easy. That is very easy. Let's just quickly do one of the question, and then we should be able to do the gate question also, right? Okay. So let's see what they are asking in this question. This is the one MSQ that I have, and then they are saying this is one university question that I've taken. Now what they are saying, indicate the ports or the edges that are not selected by the spanning tree protocol. So which means B3L4, B3L4, is this not selected? That's what they are saying. Okay, not selected. So should we do it? Maybe we can do it very quickly, right? Just for the sake of practice. So let's just do it quickly. What is the root? This is the root. Now for every bridge, let's just find out the root port. For B2, obviously this is the root port, right? So let me just, instead of writing RP, or okay, let me just write RP, no problem. Okay, for this bridge, I found out the root port. For this bridge, I think this is B4 and B1, this is B2 and B1. So if it is having two options, then I will prefer the one which is having lower ID. So this is the root port, right? For B4, it is directly connected. This is a root port. For B5, it is connected to it is connected to this bridge only, right? So this, you will say this is the root port. For B7, this is the root port. For B6, it is connected to B3 and B2 and then B1, and B4 and B1. So since it is having just B4 away, this is the root port, right? Now for each line, let's quickly find out what we call it, designated port or designated bridge. For this line, which bridge you will be selecting? I think you will be selecting this B3 or B6. Which one you will be selecting? B3 is B3, B2, B1, B6. Okay, B6 and then B4, B1. B6, B4, B1 or B3, B2, B1. I think since both are having the same distance, you will be selecting for the B3. So for B6, for this line, what I'm doing, for this LAN we need to select. For this, since this LAN is connected to this port or this port, so you will be selecting this, since it is connected to two bridges, B3 and B6. So you will be selecting B3 because both are the equal distance away. B3, B2, B1, B6, B4, B1. So that's why you will be selecting designated port. C is done. For D, not this C. For L2 is done. Let me start with L1. For L1, you will be selecting B1 or B3. I think you will be selecting B1. So this is the designated port. L2 is done. For L3, Which one is the designated bridge? Only this B directly, right? B1. So this is the designated port. And now for L4 you will say B3 or B4. This B3 is connected to B2 and then B1. B4 is directly connected, so L4 is this one. For L5, you will be selecting B1 or B4. Definitely B1. And for L6, B6 or B4. Which one will be the designated bridge? B4 is connected directly, so definitely this one, designated port. And L6 is done. L7, for L7, B5 or B4, so B4. For L8, B5, B4 or B7, this one only, designated port. L8 is done. L9, B5, B7, which one? B5 and B7 both are equal, but that's why I will prefer B5, which is having lower ID. L9 is done. L10, only one is option. L11, only one is option. Yeah, that is fine, right? So which one is neither root bridge or not root port or not designated port? This B3L1, right? This one, and what else? So this bridge B3L1, this bridge having everything connected, okay. This bridge everything is done. For this bridge, this one, right? So B3L1, B3L4 and B7L10. B3L4, B7L10, not L9. So A is the answer, right? So this three are the answer. So you can find out that B3L4, B6L2 and B7L9. So these are the answers. Okay. So I hope that is fine to everyone. So that's very easy algorithm. Like once you practice, you can do it. Now this is the gate question. I'm not going to do it. You can just do it. You just designated the root bridge. I mean, this is the root bridge, and then from this you just find out that for each bridge what is the root port, and then for each line what is the root, what is the designated port, okay, or the designated bridge. Cool. You can do it. And then they are saying that you do it, then you draw the spanning tree, then you take the DFS of the spanning tree and then see which one is the correct answer. Okay. Now let's just start with error detection and error correction, which means particularly in today's lecture we are going to see Hamming distance and the CRC. In depth we are going to see, conceptually we are going to see, and we will be solving as usual PYQs, because that's the focus. Let me know if there is any confusion till this point or everything is going smooth. Yeah, sure, Vishnu. So Vishnu is saying that please cover all India mock test questions of the computer networks today only. Yeah, definitely we will be doing it. Yeah, thank you for your feedback. So he's saying mind-blowing test and questions. Please discuss solutions live. Yeah, we will be doing it. Today I will solve CN questions also, but at the end of the sessions. Okay. It will just take 10 to 15 minutes, but we will be doing it. Okay, cool. So let's just start with our error detection and error correction. Let's just take 1 minute of drinking. So meanwhile, you can ask me if there is any question while I'm having some. This bottle is from Amazon. I mean, this is very small bottle and I like it. This is for the Amazon Machine Learning Conference. I think name is also not showing clearly. It is AMLC, Amazon Machine Learning Conference 2020. So this, as you can see, at that time it was a COVID time, so that's why it was a virtual conference. So it is written here virtual conference. Okay, great. So you can hear me, right? So let's start. Let me know if there is any doubt. Otherwise, we can start. Good. So there are different type of errors. One is the single bit error, another one is a burst error. Single bit error means that if the if only one bit is getting corrected, I say it is a single bit error. Burst error means if multiple bits are getting corrupted, we say it is a burst error. Okay. So Joy is asking that I'm in the first year Mumbai University Engineering. How should I start my GATE CSE preparation? So Joy, I think you should enroll in the Go classes first. That should be your first step. Anyway, that is just a part of joke. So like we will answer this question maybe later. You can just comment it out and I will just answer in the comment section. Okay. So there are two type of errors. Burst error is basically saying you are having multiple bit of error. So let's suppose if this 0 1 and this is the these are the bits that are getting error, and this is the first bit that is getting error, this is the last bit that is getting error, then I say this is the burst error of length L, right? We say this is the burst error of length L, where the length L is basically number of bits from between the first bit and last bit. Now you will say that in between these bits are not affected. That is okay. I mean that's how the burst error is defined. I mean if the first bit and last bit is having the distance L, we say that is a burst error of length L. Now like what we need to do, we need to do some error detection and some error correction. But for that we need to code the data, which means whatever the data we have here, the data should be having some extra bits. That's what we call it coding the data, which means it has to be converted to something called as code word, and we call it a data word. Okay, so that has to convert it to code word, and there are two methods to convert to code word. One is a block coding, another one is a convolution coding. Convolution coding is not in GATE syllabus, and whatever type of coding we have is called block coding. So what is a block coding? Is basically appending some parity bits. Now you may append the parity bits at the end, or you may also append the parity bits in the between, which means that if you are having some message bits, you can append the parity bits in the end. That's also a block coding. Or maybe you can append the parity bits in the between. That's what we do in the Hamming distance. That's also a block coding. So whatever the type of error detection and error correction we have, that's just a block coding. So in the GATE syllabus you have block coding only, and particularly here you have single bit parity, checksum, CRC, Hamming distance, Hamming codes. So all of this we have in the GATE syllabus. Now, what do I mean by error detection? Error detection means if you are sending some packet, and let's suppose this is the packet that you are sending, which is basically you always send, you have the data, then you always convert that to a code word. You are sending some code word. Okay, you always send some code word to from, let's suppose this is a sender, and then the sender sends a code word to a receiver. Okay, suppose that whatever you have sent may be exactly reached by the receiver, or maybe there is some error. Now, which means if you are sending, let's suppose you are sending 1011, and if 1011 has been received, then you will say that the data is fine, there is no problem with the data. But if something else has been received, okay, something else has been received, then you will say that there is some error in the data, which means let's suppose that you receive maybe 1000. Okay, suppose something like this, then you will say there is some error in the data, and that's our goal, right? We need to detect that error. Now how to detect the error is basically one of the major problem, and we will solve this problem. So let's just see the general idea how to detect some error. How to detect some error. So basically, if you are going to send some packet, then you need to convert that to a code word, and the set of code words, let's suppose this is C1, C2, C3, these, or C4, these are the set of code words that you have. Let's suppose C1 is 1011, C2 is 1000, and C3 is 1110, and C4 is 101. Okay, let's suppose these are the only possible code words that you have. Suppose you are sending C1 1011, but it gets converted to, let's suppose it gets changed, this 0 is getting changed to 1, and then it is getting changed to 1111. Okay, this is sender, this is receiver. Now you need to understand the setup. This is sender, this is receiver. Now these are the set of all possible code words. Okay, this is set of all possible code words, right? This is set of all possible code words. Now interestingly, this set of all possible code words is known to sender and the receiver both. Okay, and that's the only way to detect the error. So now, since this is set of all possible code words, now this is basically known to not only just to sender but also to the receiver. Now whenever receiver gets some data, what does the receiver do? Receiver says that okay, if I'm getting some data, then I will check that against all of the set of all possible code words that I have. So receiver will say, let me check this 1111 with this C1. Okay, this is not matching with C1. Let me check this with C2. It is not even matching with C2. Let me check with this C3. It is not matching with C3, neither with C4. So I will say that this is not a valid code word. Not a valid code word, right? So I will say this is not a valid code word. And now if it is matching with someone, then I will tell you the scenario. So I will say that there is an error. So that's how the error is detected. How? Receiver will be comparing with some other code words and it will check that okay, this since this is not matching with any of the code words that I have, that's why it is not a valid code word, right? That's why it will say there is some error. There is some error. Now, let's consider a different scenario where you are sending, let's consider a different scenario where you are sending 1011, okay, 1011, and you are also receiving 1011, which means you are receiving 1011 only. Now, what the receiver will do? Receiver will do the same thing. It will check against 10 with this C1. It will say that okay, it is matching with one of the valid code word. Then it will say that it is a valid code word. It is a valid code word, right? And as per the receiver, since it is a valid code word, as per the receiver, there is no error. Okay, receiver will say there is no error. That's very interesting, right? Receiver will say there is no error, and actually there is no error because this is a valid code word, and this is what we sent. But that's not the way to detect that error. Maybe if you are sending 1011, let's suppose it receives 1110. Then tell me, is this a valid code word? Receiver will say it is a valid code word, so receiver will say there is no error. Okay, so here receiver will say that there is no error, but in reality there is an error, right? In reality there is an error. So that's called that we are not able to detect that error. So receiver is not able to, in reality there is an error, so that's why you will say receiver is not able to detect the error. Receiver is not able to. Right? Okay. Thank you, Shivadeep. Yeah. He's saying Sachin sir has done literally so many things in life. Gate topper, work at big MNC, founder. Yeah, like I mean, after topping the gate or after securing very good get rank in the gate, then everything becomes very easy. So gate is actually a gate to many of the paths, and I will say that gate is quite underrated. I mean, in India, I mean obviously in India gate happens, so it is very underrated exam, and I mean people consider it either tough exam or they do not value it much. But I think that it is very nice exam. It can change your life for forever. It can give you the opportunities that you cannot even uh, dream of as a BTech student. So it has a pathway to all of the things. Like I mean, it is very powerful exam. It gives you all of the opportunities that any of the top institute in the foreign gives you. I mean, not all obviously the Stanford, MIT, if I just leave them. Like you just talk in the terms of MS. If someone is going for the MS and even they are going for the very good universities like for example maybe the University of Buffalo or University or NUS or NYU, okay, New York University or University of Singapore or something like that. then also they are also getting the same opportunity that you are getting. The reason is very simple. I mean, why I'm saying so, because see, if they are like, let me just say, like, let's suppose they are coming to the India and they want to work in some company, then they will be working in the same company that you are working. Reason being is that you are already working in the top company and they will also work in the same company. Where else they will go? So if they come to the India, then you both are at the same level, right? And if you go outside, then obviously you will also be getting the same opportunities that they have gotten, because I mean, it obviously depends on the individual potential, but in general, like these IISCs and the many of the top universities in the world, these are having the same potential. I mean, they also follow the same curriculum. Yeah, although their rankings are not too much good, because of there are many other factors, and computer science is not only one department that they have. There are some other departments like biological department, science, physics, chemistry, and there are some other departments. Overall the ranking is there, but even in the CSE, if the ranking is low, then it doesn't mean that Indian institutes are any lesser than any top institute, because the ranking is not only based on the, you know, the research papers, or not only based on the funding. It consider many things, and obviously, like, we do not have that much fund, we do not have that much international exposure, so that's why the Indian universities are not having that good ranking. But I personally think that if someone is going for MS or someone is going for MTech, then I don't think there will be any difference after completing the degree. So I mean, that's my personal opinion. Maybe it might differ, but yeah. So anyway, let's just continue. So now let's suppose you are sending something, and receiver is receiving something else. Now there could be two cases: either the receiver is receiving a valid code word or an invalid code word. If it is an invalid code word, then there is definitely some error. But if it is a valid code word, then there could be error or there could not be error. See, here there is no error and this is a valid code word, but even though this is a valid code word, still there is error, right? So in some cases, receiver may not be able to detect the error. If whatever you are sending, that is getting converted to a valid code word, then receiver will not be able to detect the error, right? Now let me ask you a question, maybe here. Okay, so let me ask you a question, a true false question, a very easy question. If receiver receives an invalid code word, then there is definitely, tell me if this is true or false. Tell me if this is true or false. Okay, and also let me ask you a question. If receiver receives a valid code word, then there is no error basically. Tell me. See, if receiver is receiving an invalid code word, then definitely there is error. So that's true. But if receiver is receiving a valid code word, it doesn't mean there is no error. There may be error, right? So that's false. I hope you understood. Okay. Um, Pinnacle Gaming is asking, sir, I'm scoring 55 plus, 55 plus in the mock test. How much I can expect in the real examination? In the mock test, like, if you're like, actually it is not very much related. Sometimes it is differing too much. If you are accessing, if you are sorry, if you are getting the 55 plus, then maybe in the gate you may get 70 plus also. I mean, it depends on the gate examination. So for me, I used to get 60 in gate, and I got, sorry, in mock I used to get 60 in mock. And in gate, can anyone tell me, like, I think I told it once or twice. So I got 78 in gate. So it was plus 6 plus 18 for me, which is a huge jump, right? So I mean, GATE is very nice examination. If you have done it very properly, then it will test your concept. It will give you the marks. Don't worry. Okay. If you have not studied and somehow you are managing to get those marks, then maybe it will not be a good exam for you in the GATE. But if you have really studied conceptually, then it will give you the marks. Okay. So let's just continue. Now there are two things that we are going to see. One is error detection, another one is error correction, right? So let's just see both of the things. In the error detection, we are going to see CRC, and in the error correction, we are going to see Hamming distance, Hamming codes. So I mean, obviously, if something can detect the error, something can correct the error, then something can definitely, obviously, the first step is to detect the error. So let me just tell you what is the difference between the error detection and error correction. Error detection is if I'm just saying there is an error. Okay, I'm just saying that there is an error. This is called error detection. Error correction is basically saying, what is error correction? That's very nice thing to understand. Error correction is basically saying that, see, there is an error and this is where the error is. Okay, it says that, see, look, there is an error and this is where the error is. Which means it will just point out two things. Let's suppose this and this bit is actually error bit. Let's suppose that this is 10101 I mean anything 001 anything. So it will say that, see, these two bits are having the error. So which means it will not just say there is an error, it will also tell that where is the error. Okay, so this is the error correction. Cool. Now let's quickly go to the Hamming distance. What is the Hamming distance? It is the number of bits, difference in number of bits between the two strings. Between 000 and 011 is having distance of 2. Similarly, it is having the distance of 3. Okay, so it is having distance of 2, it is having a distance of 3. That's called Hamming distance. Now let's go to very important, very nice concept, which is that what should be the minimum Hamming distance to detect an error. Okay, maybe let me just minimize my video size. Okay. So what should be the minimum Hamming distance for the error detection? What do I mean by that? See, understand this very carefully. Let's suppose you have some couple of code words, which means let's suppose you have 0000101. Okay, I mean this is one code word. This is 1011. This is another code word, C1, C2, C3. Some code words you have 1100, something like that, right? Now what you want to check what should be the minimum Hamming distance between these two, such that let's suppose I can detect some 2 bits of error, 3 bits of error. That's your question. Okay, so your question is that what should be minimum Hamming distance such that we detect, let's suppose, 3 bits of error. Okay, something like this. So let's just understand this carefully. So what we will do, so whatever code word we have, let's suppose that this is the code word that I have. Okay, this is a C1. This is one code word that I have, and I'm just drawing one line. You will get to understand that what I'm doing here. Now suppose that if there is 1 bit of error, then this C1 gets changed to something else. If there is one more bit of error, C1 gets changed to something else. If there is one more bit of the error, C1 gets changed to something else. And then if there is, I mean, at the 4 distance away, I do have C4. Okay, let's suppose this is the C2. This is the configuration that I have, which means this C1 and C2 are the valid code word. This is the valid code word. This is something invalid. If C1 gets, if there is 1 bit of an error, C1 will change to this. If there is 2 bit of error, C1 will get changed to this. If there is 3 bit of error, C1 gets changed to this. If there is a 4 bit of error, then C1 gets changed to C2. And C2 is again a valid code word. Similarly, let's suppose there is a C3 that I have here, okay, and if there is a similarly, let's suppose there are three dots in between, which means if C2 the 1 bit of error, it gets changed here, 2 bit of error, 3 bit of error, and then 4 bit of error, it gets changed to C3, which is also a valid code word. Okay, now assume that there is no other code words that I have, which means that only 3 code words that I have, C1, C2, C3. Just for the sake of example, I'm trying to make you understand. Okay, so learn with me is asking that what syllabus we are going to cover today. We are going to cover a whole computer networks. Okay, so it will take 1 more hour to cover me this Hamming distance and CRC. Then we will have a break of 2-3 hours. Then we will cover the remaining topics later. Okay, and I will take 1 more session or maybe 2 more sessions, but I will make sure that I have covered everything today. So that you are able to solve, and even like I can go through all the like GATEOverflow PDF where I do have all the PYQs. Then we will see that am I able to solve all the questions here or not. Okay, we will make sure that we should be able to solve all the questions. Cool. Now suppose that C1 is having 1 bit of error, then what you will be getting? You will be getting this as a receiver. Okay, receiver will be getting this. Receiver will get this. Now since C1 is having 1 bit of error, then receiver will get this. Then can the receiver definitely say it is an invalid? Because it is neither C2 not C3 not C1. That's why receiver will say that this is an invalid word, right? So that's why receiver will say that see, this is an invalid code word. So if C1 is getting changed to this, you are as a sender, you are sending C1. You are sending C1, and at the receiver you are getting this. Okay, let's suppose at the receiver you are getting this. You will say it is an invalid code word, right? You will say it is an invalid code word, and you can detect the error. So you can detect the error if there is a 1 bit of error. If receiver gets this, you are sending C1. See, you are sending C1 only. If receiver gets this, tell me if you can tell me. Receiver can tell there is an error or not. Okay, suppose you are sending C1. You are sending C1 and you got this. You get this. You get this. You are sending C1. You get this. Tell me, can receiver say that this is invalid or not? Or I mean, there is an error or not? Yes, definitely, because since this is invalid, that's why receiver will say that there is an error. Right? There is no question in that. Let me know if that is clear. Right now, since now let me ask you, what if the receiver gets this? What if the receiver gets this? Not this one. What if the receiver gets this? Can receiver tell that there is an error? Yes, which means if there was a 1 bit of error, then receiver can tell there is an error. If there is a 2 bit of error, then receiver can tell there is an error. If there is a 3 bit of error, then also receiver can tell there is an error, because these are invalid. That's what I'm saying, right? Now suppose that receiver get this. You are sending C1. Remember, you are sending C1 and receiver gets this. If receiver is getting this, then if receiver is getting this, then can receiver say there is an error? Can receiver say there is an error? This is my question now. Let me know. Obviously no, right? See, receiver is getting a valid code word. Whenever you get the valid code word, you don't know whether there is an error or not, right? So now you will get confused with whether there is an error or not. So that's why you will say, if you are getting the valid code word, you cannot say. So you are able to detect 1 bit of error, you are able to detect 2 bit of error, you are able to detect 3 bit of error. Because if you get it, it means there is a 1 bit of error. If you get it, there is a 2 bit of error. If you get it, there is a 3 bit of error. In all of the situations, you were able to tell me that yes, there is an error. But once there is a 4 bit of error, you are not able to tell, right? So if the distance is 4, then you can detect up to 3 bits of error. Up to, why I'm saying up to? Because even if there is a 1 bit of error, you can tell. Even if there is a 2 bit of error, you can tell. Even if there is a 3 bit of error, you can tell. So if the distance or the minimum distance means among all the pairs, so I will say minimum distance. So so let me just write it here. If minimum Hamming distance is 4, then it means what? It means this is a scenario, right? If the minimum Hamming distance is 4, then receiver can tell whether there is a 1 bit of error, 2 bit of error, like that, right? So it means this scenario is like this. then receiver can detect up to 3 bits of error. Now, I hope you understood this. Now let's consider the very nice situation, very I will say very favoring situation that is in our favor. Let's suppose I have a system, okay? I have a system where my system or my channel. Let's suppose I have a channel. I mean, this is at the channel point of view. The channel can produce at most 3 bits of error. I mean, this is what channel capacity. Channel is bad channel. It's not a good or noiseless channel. It is a noisy channel. Okay, obviously it's a noisy channel, right? I mean, I do have a noisy channel that can produce 3 bits of error, at most 3 bits of error. Then what will I do at my end as a programmer? Okay, as a programmer, what will I do? As a programmer, what will I do? I will say, see, channel is bad. It can produce the error, but let me see that how many bits of error it can produce. It can produce 3 bits of at most error. As a programmer, what will I do? I will design a Hamming code word. I will design Hamming code words, Hamming words, such that minimum Hamming distance is 4, isn't it? So that I can detect all the errors. Distance is 4. See, I am way smarter than my channel. If channel is bad, then I am also worst. Okay. So anyway, I am remembering one movie dialogue, but it is not appropriate to say it here. So that's why. Okay. So as a programmer, I will design a Hamming code word that is basically having a distance of 4, so that I can detect all the errors. That's the thing, right? Okay. Cool. Now let's move further. So basically, in general, if I want to detect if the channels can produce, let's suppose, t bits of error, then I will be having minimum Hamming distance of t plus 1, so that I can detect all the errors. In other words, okay, in other words, to detect in order to detect t bits of error, I can say we need d minimum is equal to t. See here, although this is not very necessary to know, but it is good that you know one thing is that these errors are of channel property. Okay, I mean, channel is producing how much error, this is of channel property. This minimum Hamming distance is is under my control, because I am designing my protocol. Okay, so what will I do? I will see the channel, whatever number of errors it can produce, I will make the minimum Hamming distance just one greater than that, if I want to detect all the errors that channel can produce, right? Okay, so see, the s plus 1 or t plus 1 is the answer. Now let's see an interesting part, which is, can we even correct the error? Can we even correct the error? Let's just check it. What do you think? Can we correct the error? By correcting, what do I mean? By correcting, I mean that I mean, I can even tell that the error is at this bit, which means I can say that, see, this is the code word that you have got, and I will say this is invalid. Okay, this is invalid, and 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 I can fix it. I can fix it basically. Okay, which means I can tell you that what is a valid code word. So that's called the error correction. Now tell me, can you correct the error? I mean, if you can, then how? That's very nice method. Let's just see that how we can even correct the errors. Suppose that this is again a number line that I have. Suppose that this is a valid code word. Now let's suppose again, Again the same case where I have 3 invalid in between. Okay. And then I do have, let's suppose, C2. Again the same case, right? So 3 invalid, maybe more than 3 but minimum 3, and then I have C3, something like this. Now suppose it is given to me, okay, suppose I know a channel better than I know myself. Okay, better than, I mean to say that I know that my channel cannot produce. So I know, let's suppose my channel can produce only 1 bit of error. Then let's just see if using this setup, the setup that I have below, then I can detect the 1 bit of error or not. Which means if I'm transmitting C1, then can you tell me what are the possibilities at the receiver side? If the channel is just producing 1 bit of error, then what are the possibilities at the receiver side? Receiver will say that either it will be receiving C1, which means no error, or it will be receiving this, right? At the receiver side, either you will be receiving C1 or you will be receiving this one, because my channel cannot produce more than one bit of error. It will just no produce any error, or this one, right? So see, if I'm sending C1, then there are two possibilities: either I receive C1 or I receive this. If I'm sending C2, then either I receive C2 or maybe I receive this, or maybe I receive this, something like this, right? So basically, if I'm sending C2, then just see here very carefully. See, if I'm sending C2, then I can receive either C2 or just something which is 1 bit away. So I can receive this one or this one. So let me just put it in a circle. So if I'm sending C2, then I can receive these 3, right? I mean, these 3 are the only viable option that I have. If I'm sending C1, then what I can receive? I can either receive C1 or I can receive the nearby, right? I mean, just a 1 element away, or just a 1 distance away. So maybe I can receive this one, or maybe let's suppose there is one more here, which is also invalid. Then I can receive either C1 or maybe these things, right? If I'm sending C3, then either I can receive C3 or maybe this one, or let's suppose this one, which is also invalid. So if I'm sending C3, then maybe I can receive, let me use another color. Is this fine to everyone? See, every of this code word has its own bubble, and that is how we will be detecting, we will be even correcting the errors. So what will happen if I'm sending C1, then let's suppose I receive this one, okay, let me call it maybe x1, and I receive x1. Then am I sure that if I'm receiving x1, then am I not sure that first of all I will say that receiver will say this is invalid, this is invalid. Can receiver also say that this invalid corresponds to which valid? See, if I have received x1, it must mean that since I can only produce the 1 bit of error, it must mean only one distance away, whichever I have, right? C1 I have. So basically, if this is the invalid, then I must have, the valid must be C1. Valid cannot be C2. Reason being is that if valid is C2, then it has to be 1, 2, 3. There has to be 3 bits of error. Then only I must have received this x1. But there cannot be 3 bits of error. So basically, if I am receiving x1, then I will say that see, this x1 corresponding valid is just C1. No one else is the corresponding valid. Isn't it? You're getting my point? So basically, if you are receiving x1, then you are 100% sure that what is the corresponding valid. Similarly, if you are, see, you can never receive this, so you can even just remove this, because if you are sending C1, you are receiving either x1 or maybe this one. Similarly, if you send C2, then you will be receiving either y1 or y2. Then if you receive, if you send C2, then there are three cases. You receive C2, you receive Y1, you receive Y2. You C2, that is fine. If you receive Y1, you will say that see, it is invalid. And don't you also know the corresponding value? Can you say that the corresponding value is C1? To say it, there has to be 2 bits of error, but there is just a 1 bit of error in the channel. So that's why you will say the corresponding value is C2. See, so what I'm doing here is that what I know here, it is very interesting here. If I am if I am receiving some invalid, I know what is the corresponding valid also. Because here, let's suppose it is 1 bit of error, then I will say that okay, the if that is the channel can produce a 1 bit of error, then it cannot be this valid, because for this valid there has to be 2 bit of error. But since there is no 2 bit of error, then I also know the corresponding valid. So that's the core idea about the error correction, right? That's the core idea about the error correction. That's how we are going to correct the error. Let me know if you have understood this. Okay. So what we are saying here is that that whatever invalid we have, do we have the fixed corresponding valid? Now let me just write it here. Whenever we get invalid, then we need to see fix corresponding valid. That's the point, right? If we have fixed corresponding valid, then we can always detect the error. Sorry, correct the error, even correct the error. Okay, let's see some examples. Suppose that this is the scenario that I have. Okay, this is the scenario that I have, where C1 is here and C2 is here, somewhere here. And let's suppose that in between there are multiple invalids. Now suppose the channel can produce, maybe let's suppose up to 3 bits of error. Then can I correct, then can I always correct the error? That is my question. If channels can produce up to 3 bits of error, if it is producing 1 bit of error, then let's suppose you are sending C1. Okay, you are sending C1, then you can receive this, you can receive this, you can receive this for C1. For C2, you can receive this, you can receive this, you can also receive this. That's the problem. If you are sending C1, then also you can receive this. If you are sending C2, then also you can receive this, because there is 3 bit of error. So things are fine if you are receiving this one. If at this end, let's suppose you are receiving this one, you will say that the corresponding valid is C1, because that's the only valid. But for this, you will get confused. The corresponding valid is C1 or corresponding valid is C2, right? So that's why in this case, you will not be able to detect the error, right? I hope you understood. So that's why in this case, you will not be able to detect the error. So that's why I will say that in this case, in this particular case, because since you can get this, that's why you are not able to detect the error. Okay. Now let's have one more example. Suppose this is C1, this is C2. Okay. Now okay, let's suppose that I am saying channel can produce either. Okay, I will go to that question in just a minute. Before that, let me just say can produce up to 2 bits of error. Okay, maybe for now up to 1 bits of error. Up to 1 bit of error. Then can I correct the error? Then can we always correct the error? Tell me. In this case, can we always correct the error? The answer is yes, because if C1, if you're sending C1, this is the only invalid that you can get. If C2 the only invalid, basically the invalid sets must be different. Whatever invalid you can get from C1, whatever invalid you can get from C2, these should be different. These must be different, right? These must be different. If the invalids are different, then the life is good. Okay, this is C1 invalid, this is C2 invalid. If they are having their own bubble, then you can definitely correct the error. Because if you detect, if you receive this, you will say C, the corresponding value is C2. If you receive this, you will say C, the corresponding value is C1. Right? Now let me change this question. Let me say, if you are getting, let's suppose you are getting, you can get up to 2 bits of error. Okay, let's suppose you can get up to 2 bits of error. Then can you correct the error? See, if you are sending C1, you can get this invalid, this invalid. If you are sending C2, you can get this invalid. That's the problem, right? And this also. So basically, their invalids are overlapping. Since their invalids are overlapping, no, you cannot correct the error. Right? So here the answer is no. Now let me ask very interesting question. Let me say that if this is a situation, channel can produce either no error, channel can produce either no error or exactly 2 bits of error. Tell me, in this case, will you able to correct the error or not? That is my question. This is very nice question. If you tell me, then I will be quite happy. Just see if you can do it. Okay. So see, channel can produce exactly 2 bits of error or no error, which means if you are sending C1, either you receive C1 or you receive this one. If you are sending C2, either you receive C2 or you receive this one, right? So basically the corresponding invalids are still different. Since the corresponding invalids are different, that is why you will, in this case also, you can correct the error, right? Because if you receive this, you will say, see, this is definitely C1. Because it cannot be C2, because C2 is just one distance away. It is definitely C1. If you receive this, you can correct it. You can say that it is definitely C2, right? So the answer is yes. I hope you understood. So I hope that is clear that how to correct the error. So to correct the error, you need to have the set of different invalids. Now suppose I want to correct up to 3 bits of error. Then what should be minimum having distance? Okay. So don't use your formula that you already know. I know that you know the formula, which is good thing, but let's just understand this first, then we will see the formula. See, if channel can produce up to 3 bits of error, I want to detect up to 3 bits of error, let's suppose, which means this, if I'm sending this, maybe I said I receive this, maybe I receive this, maybe I receive this. These are the 3, right? If I'm sending C2, then I should be having different invalid. That's the case. I should be having different invalid. So C2 cannot be here, because C2 is here, then this invalid is actually overlapping. So that's why if I'm sending C2, then there are different invalid for C2. For C2, these are the 3 different invalids. These are the 3 different invalids. And there has to be a separate boundary between these 2 invalids. These are the invalids for C1, these are the invalids for C2. These are the invalids for C1, these are the invalids for C2. Okay, if I can do this, then I can definitely correct 3 bits of error. Because if I receive this, I'm sure that it is C1. If I receive this, I'm sure that it is C1, because I can produce at most 3 bits of error, and this is 3 bits away from C1 but 4 bits away from C2. So that's why it cannot be C2. So if my invalid sets are different, then if there is a strict boundary between the invalid sets, then I can definitely correct the error, right? So there has to be a strict boundary. So which means, see, this is definitely 3, right? I mean, these are 3, this is 3, and there is just 1 also, because at least one boundary should be there. You can have multiple invalid. I'm not saying that there is one. Okay, you can have multiple invalids here also, but at least there should be one distance. I mean, these two should not also overlap. There should not be 0 distance. Okay, so basically, if you want to detect, in general, if you want to detect t bits of error, then d minimum should be, if you want to detect t bits of error, then d minimum should be 2t plus 1, right? Sorry, correct, not detect. I'm sorry if I'm making this mistake. So I only mean correct. Okay, 2t plus. I only mean correct. Yes, Jeski, that's correct. So number of invalid between two valid codes must be 4. Hence d minimum is 4. No, number of invalid between two must be at least 1, 2, 3, 4, 5, 6. 6, right? Yeah, that could also be a nice question. Thanks for giving me a question. I mean, we can ask this question in some of the test. So what should be the number of invalid codes? That's very nice question, right? I mean, people might mark it 7, but that's not 7. Number of invalid codes between two valid should be at least 6, not 7. Okay. So yeah, that's very nice question. So if you want to detect, if you want to correct, sorry, if we want to correct up to 3 bits of error, then number of invalids between two valid code words should be at least, right? It can be more than 6. That's not a problem. Okay. So in general, this is the formula 2t plus 1. I hope you know the formula, but now you know how to come up with this formula. Okay. Now let's just move to the different topics. I mean the questions, and then we will see one more thing in the Hamming distance, which is quite important. Then we will see some more techniques, which is CRC and all. Right. So let's just do one thing. Maybe we can start after a lunch break. Okay. So let's just see that I mean, there is very important things that we want to cover in the Hamming distance also. I mean, how to construct that Hamming distance, that you might be knowing, but there is very nice thing, which is basically that how this Hamming distance are working basically. I mean, okay, so there is one formula, there is 2 power r is greater than or equal to m plus r plus 1. You might know this formula, but today we will see how to drive this formula, just like we have derived these two other formulas, which is t plus 1 and 2t plus 1, right? So let's just have a lunch break, and we will start after 2 hours. Okay. So I will schedule I will schedule a session on the YouTube channel only. Okay, you can join that session. There we will first quickly finish the Hamming and CRC. Then we will start the network layer. Okay, network layer we will start. So from maybe 4:30 to maybe 7, we can cover the network layer, and then from maybe 8 or something, maybe 8 should be the good time. 8 to 11 we can cover the transport layer, and then yeah, in between also we will be covering the application layer protocols. So basically if we go till 11, then everything should be covered. Okay. And then I will go through all the PYQs. I will show you the PDF. Okay, I will show you the PDF. I will go through all the PYQs, and we will just check that, we will just tick mark that okay, these PYQs we have covered in the sense these PYQs we can solve using the concept that we have just seen today. Okay. So that's the plan. Cool. So let's just meet at 4:30. Thank you everyone. Take care. Bye bye.